to be very interesting, and some of you have messaged me that we want to know little more about fractals and fractal interpolation functions, and what will be the Hausdorff metric and what will be the Hausdorff space. So whenever you are going to work on fractals, then you must know about this space, the space where fractals live. So the outline of my talk consists of history, then definition of Hausdorff distance, then Hausdorff space, and completeness of the Hausdorff space. So this is the person, and the name of the person is Pompeo, and you can see his reference, and he wrote this paper in 1905, and he was doing something, and for that he needs some distance. So in his arguments in the complex plane, Pompeo needed a notion of distance between closed curves. Now you can see here, let E1 and E2 be two compact, compact means closed and bounded sets in the Euclidean plane R2, and if x belongs to E1, then we have to define some distance. Okay, so the first distance we are defining d of x comma E2, and this is like minimum of modulus of x minus y such that y belongs to E2. Then what will be d, capital D of E1 to E2? Okay, so E1 to E2 will be maximum of this distance, d of x comma E2. So what will be d of E1 comma E2 will be maximum of d of x comma E2. That's why we write, right, maximum then minimum of modulus of x minus y such that y belongs to E2. Then the reciprocal or Pompeo distance P means this Pompeo has defined this distance, like in Hausdorff metric. You know what is the Hausdorff metric? Suppose h of E1 comma E2, right, that will be maximum of d of E1 comma E2 and d of E2 comma E1. So in coming slides we will see that this Hausdorff metric or distance will be equivalent to this Pompeo distance. Okay, so first time he Pompeo described P of E1 comma E2 is equal to sum of these two distances, d of E1 comma E2 plus d of E2 comma E1. And for more reference you can see this paper from in 1806 by Jean Robert Argand. So I will go little further. Now you see here the one important property, if E1 is subset of E2, in both the figures you see. So in the first figure two concentric circles are disk, so E1 is contained in E2, so the distance capital D of E1 comma E2 will be 0. In the second case also, means rectangle is inside the circle, there also d of E1 E2 will be 0. So if E1 is subset of E2, then capital D of E1 comma E2 will be 0. Then after that Frachet came. So already you know that Frachet introduced the definition of metric. So already you know that this is the preliminary what is the definition of metric. So let X be a non-empty set and let D such that X crosses to R, you can take R positive also, be a function that satisfied the following axioms. So first axiom is non-negativity, D of X comma Y greater than equal to 0, and D of X Y will be 0 if and only if X is equal to Y. And the second property is symmetric property, d of x y is equal to d of y comma x. Then third property is triangle inequality, d of x comma z less than equal to d of x comma y plus d of y comma z. Then this d is said to be a metric on x, and the pair x comma d is called as metric space. And you can see the reference by M. Frachet in 1906 for this metric and metric space. Then after that this Felix Hausdorff came, and he has given one statement: in the natural setting of metric space S comma D with a small modification, the sum replaced by the maximum. Like in Pompeo what he has taken? D of E1, capital D of E1 comma E2 plus D of E2 comma E1. And now Hausdorff what is doing? He is just replacing with the addition he is replacing with maximum. Then H of AB is maximum of D of AB comma D of BA. So Hausdorff established that the Pompeo metric P of AB between compact subsets A and B of X gives the same topology as that of H of AB. That is, they are equivalent and hence called Hausdorff metric. So anyone can tell me the definition of equivalent matrix? Suppose we have two matrix D1 and D2, two matrix, and I want to say that they are equivalent. So I say that if D2 is equivalent to D1, then there must exist some constant C1 and C2. This happens, right? Clear? So now you have one Pompeo P metric and you have one Hausdorff metric. Okay, and you are saying that both are equivalent. Then we have to see that there are some constant C1 and C2 existing, there are not. So here you see that how will you calculate D of AB and D of BA. So you see that blue color is B and that green color is A, and I just depicted, I was trying to show that, means what will be the D of AB. So you see here this part is your D of AB and this part is D of BA. So like suppose you are doing PhD at IIT Madras or IIT Delhi and you have to give one comprehensive exam, and in comprehensive exam they check you very thoroughly. Okay, like again you are doing your GATE exam or JRF exam. So in that exam they give you all the syllabus of JRF and GATE and they will ask that what are you studying here? You say that fractal. So they know that fractals are living in the Hausdorff space. That means you know D of AB and D of BA. And in your DC committee member, suppose our means very reputed professors like Thamman Nair sir or Kulkarni sir is there, they will 100% ask these questions. Okay, I will give you one set A and B, you find D of AB and D of BA. So you just see that D of AB is nothing but supremum X belongs to A, infimum Y belongs to B, D of X comma Y. And we will see some questions. We will see some questions where we can see how we will calculate this. And this D of BA, supremum Y belongs to B, infimum X belongs to A, D of X comma Y. Now I am saying that D of AB is not equal to D of BA. Okay. So like that you can do one exercise here. Like Atanu is there and Atanu, I asked many times Atanu to do this type of exercises. Okay. So like you can see here, this is your A and this A is like x square plus y square is equal to 1, and this is your B, and B is something x square plus y square is, let us say, 3 square. Okay. Then A is subset of B, right? A is subset of B. This means D of AB will be 0, but D of BA will not be 0. Okay. Where?
X square plus y square is equal to 1. Just
Ha. Now fine. Okay, so D of AB will be 0. Means I am just saying A is subset of B here. Okay. But D of BA will be some number greater than 0. So that means D of AB is not equal to D of BA. So like here I am saying D of D of AB is not equal to D of BA. So So now here we want to say that Pompeo Hausdorff metric. So like I told you that when two metric are equivalent, there must exist some constant C1 and C2. So I am writing this thing. You write maximum of 2 u comma v, maximum of u comma v is always less than equal to u plus v, right? Means 3 and 7. Then maximum of 3 comma 7 is 7, and that will be less than equal to 3 plus 7, 10. And this quantity will be always greater than the arithmetic mean, you can say, u plus v divided by 2, right? Now this will be, you said that maximum of d of a comma b and d of b comma a, right? This is your h of a comma b, and here d of ab plus d of b, means you write u as d of a comma b and v as d of b comma a. Then this will become h of a comma b, and this will become p of a comma b, this will become p of a comma b, and again this will become p of a comma b. So what did we conclude? That this is your C1 1 by 2 and this is your C2 1, like here I have written, right? So that means what? The Pompeo and Hausdorff metric both are equivalent. Anyone is having any doubt or question here? Clear everyone? So Hausdorff cited correctly Pompeo's contribution, and in this way he explicitly acknowledged Pompeo's superiority in the first edition of his book. Okay, so means Hausdorff clearly cited that this distance is discovered by Pompeo, and I am just doing the modification in that. Instead of plus, I am taking the maximum of these two things. Okay, so I will go further. So what will be the Hausdorff metric space? So let H of x be the collection of all non-empty compact subsets of the metric space x comma d. Then H of x over H, and what is capital H? H is the d of AB and d of BA maximum, forms a metric space called the Hausdorff space in general. Okay, so if you are a beginner in fractals or in zipper or anything in fractal geometry, these things you must know. Okay, especially like the person who are working in fixed point theory, they want to find some applications in fractals. Okay, so what we have to see, that first we have to see the non-negativity condition to prove that H is a metric. Then first you find H of a comma a. So H of a comma a is maximum of d of a comma a comma d of a comma a. So maximum will be d of a comma a, and that will be 0. So by compactness of a and b, so I will give you the reference of Barnsley book, and I have that book, I will share with you in the group. So in that he has mentioned several properties. So one property is H of AB is equal to d of some a comma b. For some a belongs to capital A and b belongs to capital B. So that means H of AB will be lying between 0 to infinity. Okay, and if a is not equal to b, we can assume there is a belongs to capital A, so that a does not belongs to capital B. It follows that H of AB greater than equal to d of a comma b, and that will be greater than 0. Okay, and like that we can show the triangle inequality. So all of you try this in your notes. I will ask one question and then you answer me. Okay, so how you are writing this step? It is straightforward, but all of you please answer me how you are writing this one. So all of you please try. So you have to prove H of AB. I am just giving you one h of AB less than equal to h of A comma C plus h of C comma B. You have to prove this triangle inequality. H of AC is nothing but maximum of D of AC comma D of CA, and H of CB is maximum of D of CB and D of BC. So it is written here. Then from these steps how I am coming here, you please answer. Anyone? Is it straightforward to just apply the triangle inequality or something else more?
D of A comma C plus D of C comma B. We will write it D of A comma B comma D of B comma A. By using the Hausdorff metric definition, we get the answer. H of A comma C plus H of.
All of you try, all of you are getting this? Okay, so I am leaving this as an exercise, so all of you please see. Okay, how it will be less than equal to h of AC plus h of CB. Okay, it is looking straightforward, but it is not straightforward. You have to see. Okay.
You see, in terms of neighborhoods,
Yes, I am going.
much more simply.
Yeah, I am going to explain that. I am going to explain that. Okay. So the reference for this material is Barnsley book, Fractals Everywhere, and it is easily available online also. You can search it. Okay. So now I am going to give you the alternative definition as sir said in the case of neighborhood. So if x comma d is a metric space, then h of x I am defining C is a non-empty compact subset of x. And you know that what is 2 to power x or power set. Then I am defining the neighborhood n epsilon c. So n epsilon c means all the points in x, those who are having distance to c is less than epsilon, and c is coming from this capital C. And if c greater than 0 and c belongs to h of x, and I am defining h of a b in this way, infimum of all those epsilons such that a is subset of n epsilon b and b is subset of n epsilon a, if a comma b belongs to h of x. Before we have defined h of a b is maximum of d of a b comma d of b a. Now this is another definition, and I am taking infimum of all such epsilon such that a is subset of n epsilon comma b and b is subset of n epsilon a. Okay, and the function h, this function h is a metric for h of x called the Hausdorff metric. So this will also be an exercise for all of you. You check that how this function h is a metric for h of x. Okay, so this is second exercise for you. So please cross check this. Then I am going further. So now I am claiming that both the definitions are equivalent. So how will we say this? For any given a belongs to h of x, let the epsilon expansion of a be the union of all epsilon open balls around points in a, and it is denoted by n epsilon a. That means n epsilon a is equal to union of such balls. Clearly h of ab is what you defined in previous slide. Infimum of epsilon greater than 0, a is subset of n epsilon comma b and b is subset of n epsilon comma a, is equivalent to saying that h of ab is equal to maximum of infimum of the same thing. Okay, means from this line, same line you write here and take the maximum here. Okay, then what you will get in the next slide. Now since you have taken what you have taken, A is subset of then what will happen? Then you replace, right? Wherever A is there, in this last line, A is subset of n epsilon comma B and B is subset of n epsilon comma A. Okay? Then you replace, then you try, are you able to follow this? All of you try this thing. Last line, are you able to follow? Clear? Anyone is having any doubt here? So that means that will become maximum of D of AB comma D of BA. Okay? Then we will go a little more further and we have one definition and one lemma. Let S is subset of K and let gamma greater than equal to 0, then S plus gamma. Okay, so what we are doing? We are doing the dilation. Okay, we are doing the dilation. So we want to find S plus gamma, right? So S plus gamma is sometimes called the dilation of S by a ball of radius gamma. So what is the definition for dilation S plus gamma? It is nothing but y belongs to K such that D of x comma y less than equal to gamma for some x belongs to S. Okay? So please remember this definition, and I will share these slides today in your WhatsApp group so that you can follow them more nicely. So now you see lemma 1, let A and B belongs to H of x, and H of x is your Hausdorff space where x comma D is a metric space. Let epsilon greater than 0, then H of AB, your Hausdorff metric, will be less than equal to epsilon if and only if A is subset of B plus epsilon and B is subset of A plus epsilon. Okay, so we will use this definition in our further results. So you know, now you see A is subset of B plus epsilon. B plus epsilon means the set B is dilated by the radius epsilon, right? Clear? Okay, and you can see figures here, means figure B you can see here. I try to demonstrate that thing here in somehow. Okay, so now we go further. So the proof of this lemma will be very easy. So begin by showing that D of AB means what is H of AB? H of AB is maximum of D of AB comma D of BA. So first we have to see D of AB less than epsilon and D of B comma A less than epsilon, and we have to show that A is subset of B plus epsilon and B is subset of A plus epsilon. Then the other way we will show A is subset of B plus epsilon comma B subset of A plus epsilon, then we show that H of AB less than equal to epsilon. Then you have taken D of AB less than equal to epsilon if and only if A is subset of B plus epsilon. Suppose D of AB less than equal to epsilon, then apply the definition of D of AB. What was the definition of D of AB? It is maximum of D of A comma B such that A belongs to A less than epsilon. If the maximum of something is less than epsilon, that means D of A comma B less than equal to epsilon for all A belongs to A. That means what? For each A belongs to A, we have A belongs to B plus epsilon. That means A is subset of B plus epsilon. Suppose very elementary thing, if you say that A is subset of B, so that means what? How you prove A is subset of B? You take x belongs to A, and if x is in B, that means A is subset of B. So you take x belongs to A, then prove that x is also in B, then A is subset of B. So I am trying to do the same thing here. Okay. Now suppose A is subset of B plus epsilon, then what we have to consider? D of AB is nothing but, again I am writing the definition, maximum D of A comma B such that A belongs to A. let A belongs to A, since A is subset of B plus epsilon, there is a B belongs to capital B such that B of A comma B less than equal to epsilon for all A belongs to A. Hence D of A comma A less than equal to epsilon. This is true for each A belongs to A. So D of A comma B less than equal to epsilon. Okay. So we have proved this lemma. Then we go little further. So like when you are studying some papers in fractals, in means our group or any group like Viswanathan sir from IIT Delhi and MGP sir from IIT Guwahati, okay, so they are using H of AB always, okay, but it is not like that. There is only D of A comma B, D of B comma and H of A comma B. There are many other distances also, okay. So if I define the first distance, you see, let X comma D be a metric space, and if A comma B belongs to 2 to power X power set, we define the generalized functionals D1 comma D comma H comma D2 and all from power set into power set 2 R plus as follows, okay. So I am taking first distance. What is first distance? It is D1 A comma B, okay. Before that D of A comma is here. Till now we were discussing about D of A comma B and D of B comma A. So D of A comma B is clear to everyone, right? This thing is clear to everyone. H of AB is maximum of D of A comma B and D of B comma A. But there are two more distances, D1 and D2. Okay, so D1 is nothing but infimum of D of A comma B such that A belongs to A and B belongs to B. All this kind of distances and you take the infimum. Okay. So we will see like set A is here, set B is here, okay, set B is here, and there are many points, right? Infinitely many points here, also infinitely many points, okay. Then you are for each points you are finding the distances here. So there will be infinitely many distances and you have to take the infimum, okay. Then for any particular point, suppose if A naught belongs to X, then D of A naught comma B will be D of A naught comma B. Then what is the D2? D2 will be take the supremum. Take all the supremum. Here you have taken the infimum and here you have taken the supremum. So here D1 is called the gap functional between A and B. So D1 is called the gap functional between A and B. D is the excess functional, excess of A over B and B over A respectively, and H is, you know already, Pompeo-Hausdorff functionals, and D2 is called the diameter between A and B. Okay. So diameter means, diameter in real analysis you have learned about this, right? Maximum distance between two sets A and B. So I am calling it diameter between A and B. So I will go a little further and you see here. So recently my first PhD student B.V. Prithvi, and he defended his thesis. Now he is Dr. Prithvi. So he wrote one paper, interpolative operators, fractal to multivalued fractal, and it appeared in Chaos Solitons and Fractals in 2022. And we have given this type of one result to compare all kind of distances, which is greater than to which distance, okay. So we found that D2 A comma B is always greater than equal to H of A comma B, and H of A comma B is nothing but maximum of these two distances, and here D of A comma B, D of B comma A, D of A comma B will be greater than to D of A comma capital B, and this will be greater than equal to D1 of A comma B. So you can see this paper and you see how we have calculated these things, and I will take one or two examples in my future slides, and I will show you some things to you can relate here, okay. So like I have taken a set A and set B, and set A is here and set B is here, and I am taking only finite set, okay. Set A are having only 5 points, A, B, C, D, E, and B is also having some finite points. Means here I have showed infinitely many points. It will be difficult to calculate, right? So first we understand for finitely many points. So you see here, I am finding D1 A comma B. So d1 a comma b means minimum of distance of d of x comma y such that x belongs to a and y belongs to b. This means minimum of d of a comma b, all the points, right, in b, in a, from a to b, b to b, c to b, d to b and e to b. Okay, like this one. Then you can find here d of ab, d of ba. D of ab means maximum of these things, d of ba maximum of b, f to a, g to b, h to c, I to d, j to e. Okay, a simplest examples I can show you here so that you can start visualizing the things and you can relate. Okay, then h of a will be maximum of these two distances, d of a comma b and d of b comma a. Then what will be d2 of a comma b will be maximum d of x comma y such that x belongs to a comma y belongs to b. Okay, so there are some more things. So all of you first check that I take a space x is equal to 1 2 3 and I define some distances like d of 1 comma 1, d of 2 comma 2, d of 3 comma 3 0, d of 1 comma 3 2, d of 1 comma 2, like that. Is this a metric? Is this a metric? So when you are working on fixed point theory, then you can propose the theory, but examples are always valuable. Okay, right? Means fixed point theory only work on examples, right? If you give the nice examples, then your paper will be published in very nice journal. Okay, so first you cross check that is this a metric over x is equal to 1 comma 2 comma 3. And if I increase the points here, like I take 10 points, then it will be difficult to construct. Okay, and suppose now when Prithvi and Kifayat were defending their thesis, then some professors came from IIT Madras. They were asking that why you are taking finite set. For finite set also to create a metric, it is difficult task, and if you take infinite set, then it will be more difficult. Okay, so please cross check that is this a metric. Okay, and I assume that suppose this is a metric. Okay, then हाँ 2-3 की डिस्टेंस आप, इसलिए मैंने छोड़ रखा था यहाँ पे कि कोई बताए. ठीक है, तो मैं 2-3 की यहाँ डिस्टेंस नहीं दे रखी है. 2-3 की डिस्टेंस आप देख लो, 2 ले लो या, ठीक है ना. तो यहाँ पे क्या है, यस वी हैव नॉट टेकन द डिस्टेंस ऑफ 2 to 3. So d of 2 comma 3 and d of 3 comma 2 will be 2. You take, assume. In next example I have put this thing. Then what will be d1? d1 is not a metric. So what was d1? d1 was infimum of d of x comma y. So d1 is not a metric. Then you see h of x. h of x will be all 1 to all the singletons. Then 1 to 2, 1 to 3, 2 to 3, then 1 to 3. Then find d1. So I am just telling you how to find d1. d1 1 comma 2, 1 comma 3 will be infimum of d of 1 comma 1, 1 comma 1, 1 comma 3, 2 comma 1, 2 comma 3. Then infimum, whatever distances it is given in the question or in example you put here 0, 2, 1, 0, take the infimum, the answer is 0. So I am giving you one example how to find d1. Okay, and 1, 2 and 1, 3 are distinct elements, but the distance is 0, so that d1 is not a metric. You got the point? What is the metric definition? d of x comma y is equal to 0 if and only if x is equal to y, and here you are getting d1 of these 2 points is 0, but this is not equal to this. So the first definition of metric is not fulfilling. That means d1 is not a metric. Now we'll say same way you can say that d2 is not metric. d2 means what? Take supremum, then h of x, and here also we have found the d2 of 1 comma 2 and 1 comma 2, same point I have taken, and you are saying that here you are getting, you must get 0. If d2 is a metric, then you must get here 0, but you are not getting the 0, you are getting the 1. Okay, so that means d2 is also not a metric. Okay, then we go further. And these are the properties of Hausdorff metric. So means some of the properties I have quoted here. If A belongs to closure of A, if and only if D of A comma capital A is 0, and D of A comma capital A is equal to 0 if and only if A belongs to A. So this type of properties you just verify. I will give you these slides, like D of A comma A less than equal to D of A comma B, D of A comma A is equal to H of A comma B if and only if A is subset of B. Okay, so these properties we will use when we will prove that Hausdorff space is complete, okay, or compact. Then this type of properties we need. So you just go through these properties and try to verify by their own. And now I have given another example. So like my student Deepak says that here D of 2 comma 3 and 3 comma 2 is not defined. Okay, so I just put here D of 2 comma 3, D of 3 comma 2 is some number 2. Okay, then you find what will be the Hausdorff space. Then I said that 1 2 3 1 2 3 1 2 1 3 2 3 1 2 3 with Hausdorff metric H. Then I am trying to find that what will be H of A comma B. This is your A, this is your B, and this will be maximum of D of A comma B and D of B comma A. So D of this one and D of this one. Now you find D of 1 comma 3. Then D of 1 comma 3 will be maximum, minimum, D of 1 1 and D of 1 comma 3. Okay, but D of 1 1 same to same point will be 0, and D of 1 comma 3 you defined somewhere as 2. Then minimum of 0 comma 2 is 0. Then you are getting 0. Then same way you find D of 1 comma 3 1. Same way you find, you will get the answer as 0. Okay, so I am just demonstrating how to find these things. Okay, so then H of 1 comma 3 will be maximum of D of A comma B and D of B comma A, both were 0, so you will get the 0. Like that you can see. Okay, you can find H of some A comma B, right? So in both the examples, H of A comma B and H of B comma A, right? They must come same. Why they must come same? Because H is the metric. Before it is not coming. No, some properties we were not getting correct. But H is a metric. H is a metric. So H will satisfy all the exams of metric, right? So now means you can take some interval kinds of things like closed intervals. So let X is equal to R, B metric space endowed with usual metric D, H of X is Hausdorff metric space with Hausdorff metric H, and now I am taking closed intervals A comma B, C comma D are element of H of X. Then what will be H? I have given Apano these exercises that suppose 0 comma 1 and 0 comma 2 and this is 1 comma 3, what will be H of A comma B, and like 0 comma 2 and here 3 comma 5, then what will be H of A comma B? Means you just create many examples, right? When two intervals are overlapping or two intervals are disjoint, if one is half is subset of other, something like that. Okay, so here you see what will be H of A comma B comma C comma D will be same way. Then this will be D of A comma B C of E, this one. Okay, this will be maximum minimum of D of X comma Y, such that this happen, and here also like this way. So we are trying to calculate this. And if you are not able to understand these things, then you just simple examples. Okay, take some closed intervals 0 comma 1 and another interval 2 comma 3 and see that sometimes they are overlapping, some they are not overlapping, sometimes they are disjoint. Then try to find what will be D of A comma B, what will be D of B comma A, then find H of A comma B and H of B comma A, like that. Okay, then slowly you will become master in that. So I have taken all of you, please verify this. Don't see the slides. You just take one interval 1 comma 2, another interval 3 comma 4, and then find the H. Okay, please don't see these answers, just see this line, just see this line. First your interval is 1 comma 2, another interval is 3 comma 4, then please find h, please find h. So if anyone is having difficulty, then please ask. And if you are having any difficulty, then you can see my slide. Everyone got this? Okay, meantime I can clean my board. Done. Everyone? Okay. So this is your extension lemma, and it is given in Mansley book, and I just read it. Let x comma d be a metric space, and let an be a Cauchy sequence of points in h of x comma h, and let nj be an infinite sequence of integers, and they are increasing 0 less than n1 less than n2 less than n3. Suppose that we have a Cauchy sequence x and j belongs to an, and that belongs to x comma d, then there exists a Cauchy sequence x and j bar that will be equal to x and j. Okay, for all j is equal to 1 2 3 so on. Okay, so how to prove this, and to prove this, like, so you always see this type of things. Okay, so suppose we want to find the distance between xm bar comma xn bar, then you just apply the triangle inequality and try to break it, right? So d of xm bar to some xnj, and xnj to xnk, and xnk to xn bar. Okay, and now you have to find this thing something epsilon by 3, this thing some epsilon by 3, and this is epsilon by 3, and when you add together, then this will become less than epsilon at the last. Okay, so now we have to see this one, and this one. Okay, so I will give you these slides, and you can see means what we are doing here, means how we are selecting nj and nk, and we are defining these distances. Okay, so I will give you these slides. And now this is our last theorem, completeness of Hausdorff metric space. So let x comma d be a complete metric space, then h of x comma h is also a complete metric space. Moreover, if an belongs to h of x is a Cauchy sequence, then its limit, its limits must also belongs to h of x. Okay, so that is the property of complete metric space, means if a sequence xn is there and if x1 converges to x, then x must belongs to that space. Okay, so this theorem or material I have taken from Mansley book, so I will share with you. And how to prove this result, and to prove this result we have 5 steps. Like first we have to prove that A must be non-empty, then we have to prove that A is closed and hence complete since K is complete. Then we have to the extension lemma, we have to apply the extension lemma. For epsilon greater than 0 there is n such that for n greater than equal to n, A is subset of an plus epsilon. Then we have to prove that A is totally bounded and thus by B part it must be compact, and then we show that limit an is equal to A. Okay, so I just give you this slide so that you can go through it, or you can see the Bansley book, means how we are proving point A, point B, and then C, and then we are combining all these things, and then we are saying that this H of x comma H is a complete metric space. Okay. So thank you, and now I will go for my another presentation. So I will talk about some fractal interpolation or fractal functions here. Okay, so now you are able to see this figure. So fractal functions are very irregular in nature. Okay, now you see this figure here, you see 1, 2, 3, 4 points, and so the curve is very differentiable or non-differentiable. So the curve is very non-differentiable. Okay, and here when I am choosing alpha is equal to 0, then this is smooth. Okay. So now we will talk about this means, and we will see also how to plot these figures. So take the data xn comma yn belongs to R2, and I am taking this notation n belongs to nn, means 1 comma 2 comma 3 up to n. It means you can say that first n natural numbers here, nn means first n natural numbers. Okay, where abscissae are strictly increasing in order, means x1 less than x2 less than dot 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 xn, and I take ln such that I close interval to its subinterval in xn comma xn plus 1 be contraction homeomorphism satisfying ln x1 is equal to xn and ln xn is xn plus 1. So these things will be little important, so just I note them down. Ln such that I is our x1 comma xn to in, and in is nothing but xn comma xn plus 1, and here n belongs to nn minus 1, right? And I am saying that is a contraction homeomorphism. Contraction you already know, the definition of contraction you know. And what is the meaning of homeomorphism? Homeomorphism, when a mapping is homeomorphism, when it is bijective and it is continuous and its inverse is also continuous. Okay, so ln is a mapping which is continuous, ln is bijective, and ln inverse is also continuous. Okay, and it is satisfying two conditions, means ln mapping first point x1 to xn and ln mapping this end point xn to xn plus 1. Okay, then I take suppose 0 less than equal to Rn less than 1 and consider continuous maps Fn, and Fn satisfying two properties. Fn of x1 comma yn is yn, and same thing. Okay, here x1 first point we are saying no, so x1 and corresponding y1 is going to yn, and Fn xn comma yn is going to yn plus 1, and Fn is contraction in second argument. Okay, Fn x comma y minus Fn x comma y star less than equal to Rn y minus y star. So I am saying that Fn is contraction in second argument. Then I am taking one collection I cross R comma Wn, and in Wn I am putting ln comma Fn. Okay, so I am calling this as iterated function system, or in short I call them as IFS. Okay, Now I construct a metric space. So I take script G as some continuous functions, and they are satisfying h of x1 is y1. And you see that when this construction was made by Bansley sir, so x1 means xn is must go to yn, right? So based on that he is mapping x1 to y1 and xn in point to yn. Be endowed with the uniform metric. So you already know what is the meaning of uniform metric, right? Maximum or supreme norm you can define. Then T such that script G to G be defined by TH of x is equal to in this way. So I am writing TH of x is equal to Fn ln inverse x and comma, what can you write? H naught ln inverse x. Okay, and for all x comma x belongs to I. Now we have to prove that this T is a contraction mapping. Okay, so how will you prove that T is a contraction mapping? So like here I can write TH of ln x. So you will get, what will you get? Fn, yes, what will you get? X comma h of x, right? Okay, then similarly you write some Tg of ln x. Tg of ln x. So Tg of ln x will be Fn x comma g of x. Okay, then try to find Tg of ln x minus Tg of ln x. Okay, and if you are taking infinity norm or means whatever, okay, then what will you get here? Fn x comma h of x minus Fn x comma g of x. Okay, but you said that Fn is a contraction in second argument in previous slide. Okay, so Fn is a contraction in second argument, then what can you see? This one, Fn is a contraction in second argument, so it will come less than equal to Rn times. Okay, Rn times what will you get? H of x minus g of x. Okay, and by that you can prove that Th minus Tg less than equal to R times or Rn times whatever, okay, h minus g. Then this will be one more exercise for all of you. You just try to think and let me know in the after lunch that here I am taking ln x, right, and here I am writing free from ln. Okay, so how is it happening? Okay, so you got that T is a contraction mapping, and your script G is a complete metric space. You can easily prove this, that script G is a complete metric space, and you are defining a mapping T from complete metric space to complete metric space, and T is also a contraction mapping. So by Banach fixed point theorem, T will be having a unique fixed point. So this equation TH of x will be what? H of x. Okay, but TH of x is what? TH of x is Fn ln inverse x and what? H naught ln inverse x. Then you take h of ln x. H of ln x will be what? Fn x comma h of x. So you got this one. So this h is nothing but your, what is h? Okay, so now here so most means extensively studied fractal interpolation functions so far are defined by the IFS. They take ln x is equal to what they take? An x plus bn or en. Okay, and fn xy they take alpha ny, fn xy they take alpha ny plus qnx, right? Qnx. Okay, then put this value here. Then put this value here. Then what will you get? Your h of ln x, what will you get? H of ln x, what will you get? Fn x comma h of x. So what will you get? Alpha n y. Y is h of x plus qn of x. Okay. So meantime you have seen many papers, someone saying that affine fractal interpolation function, someone is saying cubic, quadratic, rational, trigonometric. Okay, so they are just depending on this qn, your qn such that I to r. Okay, if you take qn is affine map. Okay, affine map. Let us say qn is equal to some, I have taken anx plus en, then you will take something, whatever, anything you just tell me, cnx plus dn type. Okay, and you replace here, then this will give you a affine fractal interpolation function. Okay, affine fractal interpolation function. Okay, or affine FIF. And if you take qn as a quadratic function, let us say qn is equal to cn x square plus dn x plus some fn. Okay, then this will give you quadratic fractal interpolation function. Someone will say that, sir, I will take qn is equal to some pn theta by qn theta. Okay, then he will get rational fractal interpolation function. Someone will say that I will take qn as some trigonometric polynomial. Okay, trigonometric divided by trigonometric. Okay, then what will we get? Rational trigonometric FIF. So whatever qn you can choose, okay, you will get that kind of fractal interpolation function. Okay, so now this construction was done by Bansley sir, then came Novosibirsk madam, Maria Antonia Novosibirsk from Spain, University of Saragossa, and what she has done, she is saying that I will take qn in this way. Okay, so I just show you that what will happen after that. So you just take qn as f naught ln x minus alpha n b of x. Okay, so before that you take let f belongs to C of I. Let f belongs to C of I, and you take qn in this way, then put, let us say this equation is star, put the value of qn, then what will you get? H of ln x is equal to alpha n h of x plus, put the value of qn. So what will you get here? F naught ln x minus alpha n b of x. Okay, so somewhere I means here I am taking g, right, and here I am taking h. Okay, so anywhere. So if I replace here ln inverse x, so h of x will be alpha n, yes, h of ln inverse x, right, plus what will you get? F of x, then minus alpha n b of ln inverse x. Okay, and this I am denoting as f alpha, right? So further they will get f alpha x, and this one you combine, this one and this one you combine, and this one you leave here. So what will you get? F alpha x is equal to f of x plus alpha n times last line, okay, f alpha minus b not ln inverse x, okay, and for all x belongs to in and n belongs to nn minus 1, means whatever h you are getting, that will become f alpha, okay, as a notation, just as a notation, okay. F alpha is nothing but your h of x, okay. So just notation I am writing f alpha x is equal to f of x plus alpha n into f alpha minus b not ln inverse x for all x belongs to in, okay. And here b is your base function, b is base function means b x1 is equal to f of x1, what f you have taken, b of xn is equal to f of xn, and b is not equal to f, means this point and this point, f can be like this, and b can be like this. This is b. They are matching these 2 points. They are matching these 2 points, but they are not equal. Okay. So by this what did you understand? Anyone? By this what did you understand? Pabjit? What did you understand by this? Anyone? Any idea? You have taken any f belongs to C of I, correct? And for that you are getting a fractal function, okay. So for any continuous function you are getting a family of functions f alpha always, okay. So when this thing came, then our fractal got more popularity, because you are now getting a family of fractal functions, right? What happened? Source? Huh? Sakshi knows, I think. Source. It will come. Okay, so for any continuous function f, you are getting a family of fractal function f alpha x is equal to f of x plus alpha n f alpha minus b not ln inverse x. And your alpha is what? Alpha is your scaling factor, right? And alpha by contraction condition it must lie between -1 and 1. Now you have many alpha. Means alpha ranging from -1 to 1. And in this equation if you put alpha is equal to 0, means you have range from -1 to 1, right? Alpha values, infinitely many values you can take, okay. And somewhere here alpha is 0. So if you put alpha is equal to 0 here, then f alpha is nothing but f. Alpha fractal function is nothing but only f. And if you vary your alpha in the range -1 to 1, you will get a family of alpha fractal functions, means you will get infinitely many alpha fractal functions. So now the thing is that suppose I take here, okay, I take 4 points, okay. Now Dr. Vijay will go for interview, okay, many places. So they will ask such type of questions. They will ask that already interpolation theory was there, okay, why did you bring this fractal interpolation theory? What is the difference? Okay. So what you have to answer that, suppose we have 4 points, and you take polynomial interpolation or zipper interpolation or anything, okay, and you draw a curve, right? Okay, you draw a curve passing through these points. This is the interpolation theory, right? Now I want a curve. Now I want a curve like this one. Okay. So what you drawn before, that curve is unique by interpolation theory. Now I am saying that you draw this curve. Now you draw this curve passing through these 4 points. Then what will you do? What you have drawn, that was unique curve. Okay. Now I am asking another curve passing through those points. Then what will you do? Either you change your polynomial interpolation to some other, like you replace by trigonometric, rational or something, okay, or you change the points. So what will you say? I will take first point here, and instead of taking second point I may shift here, and third point I may take here, and fourth point as it is. Okay, then I will trial method and I will see that my curve is passing through these points or not. Okay, but when Novosibirsk introduced alpha fractal function, now you have alpha ranging from -1 to 1, and you have infinitely many choices. Okay, and by choosing alpha from these same points, how many different curve you can, infinitely many curve you can draw, right? Okay, and maybe the curve asked by someone may coincide here for different value of alpha. Understood? And when you are taking alpha is equal to 0, then whatever classical interpolation theory was there, you will exactly get that theory. So what you got, that this fractal interpolation function, your alpha fractal functions, they are generalizing classical interpolation theory. Okay, and in the same time, by varying the value of alpha, you can get infinitely many curves. Okay, and the other thing is that I have showed you first picture. I will come it again after tea break. So classical interpolation theory only work for smooth data points. Okay, and if you have very irregular data, okay, your guide is also working on the same thing. These 3 persons from NIT Trichy and Gauri Shankar also. Okay, so means when your data is very irregular, suppose we are at NIT Jalandhar, and I just say that now onwards to 15 seconds or 20 seconds, we have to see the load of intensity at NIT Jalandhar. We have to measure the load of intensity at NIT Jalandhar. Okay, so suppose we are in this room, all the fans and all the things are working, but her guide Mary Samuel madam is inside the Mega hostel, and she may be opening her laptop, or she is switching off or on the AC or fan or something. Okay, so the load on the intensity will be like this, no? Like suppose earthquake coming here, okay, and you want to measure the intensity, then the curve will be like that. It will not be smooth, very irregular, and you want to interpolate it, then classical theory again will not work. So wherever irregularity is coming, or any function is there that is smooth, but you are finding the derivative of that and it is becoming irregular, then again classical theory will not work. Then you have to see your answers in the fractal theory. So I just stop here and we take a short break of tea. Then we will meet again and discuss some more things, and then I will hand over to sir to give some more insights in that. Okay, thank you. got f alpha x is equal to f of x plus alpha n f alpha minus b and not ln inverse x. Then we can find some more properties here, right? Means you take f this side, f alpha x minus f of x is equal to alpha n f alpha minus b not ln inverse x. Okay, then you put some operator, means take some norm or you just operate here ln also here. Okay, so ln, okay, so what will you get this that side? Alpha n mod something, and what will you get? F alpha minus b of x, right? Then this side it is coming f alpha minus f. Okay, then this side what you do? Means you can subtract f alpha minus f plus f minus b, right? Then you bring this side. Okay, so you will get something f alpha minus f less than equal to mod alpha infinity 1 minus mod alpha some f something here, right? F minus b, right? And you are saying that for any f belongs to C of I, you are getting f alpha, right? So you can define one operator also. You can define one operator, and which is taking f to f alpha. Clear? So then obvious question is f what are the properties on f alpha? F alpha is f alpha linear? When it will be injective? What will be bound on f alpha? Right? Because f alpha is here, right? You can write this. F alpha means in next step you can write f alpha of f minus f and whole thing, right? Then f you can take out, and here you can choose b can be also having many choices. Okay, like b is equal to, you can take linear function of f. So here also you will replace b is equal to lf, then f will come out and f will come out from here, that will cancel out. So you will get is f alpha bounded? F alpha bounded. Okay, so you can discuss many properties on f alpha also. Now means we have taken f belongs to C of I. You can take if f will be in LPI, f will be in Bezow space or any higher space, then what will be the f alpha? And f is in LPI, so f is having some properties on LPI. So we have to cross check that is f alpha having the similar kind of properties. Okay, your guide has done most of the work in those directions. Okay, so means you can explore in this direction. Then we can go further and we see that with variable parameters. So you see here, before we were taking fn xy is equal to alpha n into y plus qn x, and alpha n belongs to alpha n was mod alpha n was less than 1, means alpha n belongs to minus 1 comma 1. Now what you are doing, you are replacing alpha n with some continuous function. So this fn xy will become alpha n into x plus y into y plus qn x. And what we have to see? We have to find mod alpha n infinity defined in this way, supremum mod alpha n x and less than 1 instead of constant scaling factor alpha n. Then whatever equations we were having, so we were having equation g of x was alpha n y plus qn x. This type of equation was there, right? So now if you are taking alpha n as variable scaling, then here also it will come alpha n x, okay, and x will be here ln inverse x, and this y will become g. So g of ln inverse x and q of ln inverse x. And in the same way the equation for alpha fractal function, like here f alpha x is equal to f of x, instead of alpha n what will come here, alpha n of x. So you are writing here alpha x is equal to f of x plus alpha n x replaced by ln inverse, here right, f alpha minus p ln inverse x, x belongs to yn, okay. So now again the same thing you can do. If the variable scaling is there, then you can, like whatever Novosibirsk madam has done, Abansali sir has done, then by taking the variable scaling you can explore things, okay. Then I just go for so you can read this paper by Wang and Yu, and it came in Journal of Approximation Theory, a nice journal. Then we see the Bansley-Arrington theorem, and Bansley-Arrington theorem means generally you know that fractal functions are nowhere differentiable, and you want to make them differentiable some places, okay. Then what you have to choose? We have to choose the scaling factors in such a way, and so fnp means pth derivative of fn, okay. So like ln x, g of ln x is there, and you want to find the first derivative. So what will you get? G dash ln x, then derivative of ln dash x, and ln x was an x plus bn, then ln dash will be an, okay. So here an will come g of ln x into an, and each time you differentiate, then an power will increase, and then finally you have to divide that side. So that's why it is coming an to power p, clear. And they must satisfy these two join up conditions, because you have to see the continuity also. Then you will get a IFS, whatever IFS was there, I cross r ln x fn x determines a fractal interpolation function g, which will be k times continuously differentiable. Further, pth derivative of g is the fractal interpolation function determined by some another iterated function system. So ln x comma fn comma p x comma y, okay. So just take your time and just think about this and going on in this theorem, okay. And like when it was g of x is equal to alpha n g of, you can write g of ln x is equal to alpha n g of x plus qn x, okay. So when Bansley and Harrington was trying to prove this Bansley-Harrington theorem, then they have applied the integration approach. They have used the integration approach, and if you integrate here, okay, then this alpha n will come out, and you have to see only integration of g of x. But now when Wang and Yu use alpha n as variable scaling, so here it will be variable scaling, then you cannot do integration very easily, because alpha n was a constant, so it was coming out, but now alpha n is also a variable, and now you have to apply the integration by parts, and that will be very difficult. So I and means his guide Vishwanathan sir from IIT Delhi, we have done the Bansley-Harrington theorem, and that research paper came in Bulletin of Australian Mathematical Society, and you can see the proof. Means if alpha n is a variable scaling factor, then how to prove this Bansley-Harrington theorem. So we did not go by integration approach because it was becoming difficult. So we have taken some, like before also we have taken some script g, a complete metric space, we define an operator t, and we proved t is a contraction mapping, then it is have a unique fixed point, and that unique fixed point is fractal. So in the same way we have defined a space and have taken variable scaling, and we have proved that one fixed point, that will be fractal based on the variable scaling. Okay, otherwise it was very difficult. It was a challenge. We were discussing many days, but we did not get by integration approach. Then we thought that directly we proceed. Okay, so you can see that paper. Then I just show you my first slide, this figure, and you can see fractal functions means immediate application is in constraint interpolation. Okay, so like my guide Professor Chan is well known in this area, and Dr. Vijay is also here. He has also explored many papers in this direction, shape preservation of zipper and fractal surfaces also. Now he is using some Bezier curves also. So fractal interpolation is a modern technique of interpolation that share smoothness or non-smoothness, including nowhere differentiable of given data. A smooth fractal interplane, fractal spline, yes, k times continuously differentiable, can generalize classical non-recursive splines. Okay, just I have said that if Qn is affine or Qn is quadratic or Qn is rational function, then you will get affine fractal interpolation function, quadratic fractal interpolation function, or rational fractal interpolation function. And if you will put alpha is equal to 0, then it is affine interpolation, no fractal part. It is quadratic interpolation, no fractal part, and it is rational fractal function, rational interpolation, no quadratic part. So with same time we are generalizing the classical interpolation theory. Okay, and traditional non-recursive shape preserving interpolation methods fail to produce a shape preserving interpolation k times continuously differentiable. Means if the data or the interpolation techniques are having irregularity, then I am writing in the second point that traditional non-recursive shape preserving interpolation methods fail. Okay, that's why we are moving to fractal interpolation function. And apart from smoothness, a good interpolant should honor geometric properties like positivity. Positivity means, I just clean this and I just write something here. So like you have taken some points here, like you have taken some 4 points something, okay, and you want to interpolate. Okay, and when you apply any interpolation technique like polynomial, rational, trigonometric, anything, and when you plot the curve and plot the curve, then it may go down, right? Okay, and you have taken your data positive, these points are positive, means first quadrant, but your figure is going in the fourth quadrant, means the interpolant you are getting, that is not positive. Okay, so means here you are taking all yi greater than 0, y means this is x1 comma y1, this is x2 comma y2, this is x3 comma y3, and this is x4 comma y4, and all y1, y2, y3, y4 are positive. Okay, so you are having the data positive, but when you interpolated it, your data, your interpolation is non-positive. So how to restrict conditions, how to find shape parameters or scaling parameters, how to constrain them so that this part will go up. Okay, and then the next is monotonicity. Monotonicity means you have taken a monotonic data, and monotonic data means, let us say it is monotonically increasing. Let us say like this one, data is your increasing, and you are plotting the curve, and the curve may be like this, maybe like this. Okay, so some places it is increasing, then decreasing, increasing, then decreasing, right? Okay, then how to constrain, or how to restrict our scaling factors and shape parameters so that it will become like increasing. Okay, and then convex. So you have to take data, some convex data, something like that. Okay, and you plot the curve. Okay, so curve may be like this one. Okay, so somewhere it is convex, somewhere it is concave, somewhere it is convex, concave. Okay, and you have to apply this theory and restrict your scaling parameters and shape parameters in such a way that it is always convex. It is always convex like this one. Okay, and why we are doing these things? Why we are doing these things? Okay, like you see, you want to design the aircraft. Okay, you want to design. I am not an artist, but I am trying to try. Okay, yeah, I want to try. Clear? Okay, so you want to design this. Okay, and there is any mistake from your side, then this will not land safely. Okay, and it is not like that you open your laptop, open the paint and you just draw it. Okay, you have to be very precise when you are making it. Okay, so what we have done that, suppose you want to put your interpolation figure inside this box. Okay, inside this box, then you can read our work and you see that how we are compressing these things so that it is coming in a box. Okay, and same time we have also done that, means your curve will be inside the box. Okay, suppose it is going downward this side, but you restrict your parameters so that this will be inside this box. And now another problem is that suppose you have a line, and your data is above this line, and you want to interpolate again, and the situation is that, means your curve may go like this and curve may go like this. Okay, it may cross the line and come this side, but you want to interpolate your data in such a way that it will always be above this line. So again you see our work and see how we are doing these things. Okay, then we restrict our parameters so that this will be above the line, something we are doing. Okay, same concept you generalize, for means line is like this and data is here. Okay, and same way you can do. Okay, and now mix those things. Okay, mix those things. Now suppose you want to do like this, one line is this, one line is this, one line is this. Okay, and another line is this, like this. Okay, these are two lines, and in between you have taken your some data. Between two lines you have taken your data, and now you want to interpolate it, and when you interpolate it, it does not, it may come out like this, right? Okay, and you want to preserve your interpolation between these two lines. So again you see our work and you see how we are restricting our alpha scaling parameters and shape parameters so that it will be inside these lines. Okay, and this concept you use here. Now suppose you want to make the wings of the aircraft. Okay, and this curve things you extend in surface case. Okay, like this case is there, you are putting your graph inside a rectangle or box. Now you take any surface, rectangle box will become a some cuboid or something, and you are putting some surface inside that. Like suppose you want to wrap the gifts, or you are in fashion industries and you want to wrap the clothes, and your clothes you want to put in a box, then you can use our work. Okay, so means you know the dimension of the box and surface you want to put inside, then you just set the parameters, boundary C and D, something like that, and you wrap. Okay, and same way this concept you generalize, the line will become plane. Okay, and you want to insert the surface here, right? And surface must not cross these lines, right? So you can restrict by your shape parameters and scaling factors. Means I want to say that whatever work I have discussed in curve case, you can generalize it for surface case. Okay, and then if you have work for constant scaling, then you put vertical scaling, and you can generalize the curve case as well as surface case. Okay, so there are some problems like that you can do, and like suppose you are driving a car, and if you are sitting on the driver's seat and you see the front portion. Okay, so front portion is always like this, right? Where your mudguard is there, right? Okay, person is sitting here. In front of that person is always in the. So that surface is monotonically increasing, right? So if surface is monotonically increasing, that means you apply this concept. So when they design in computer geometric design, they use CAD softwares, they use these techniques, means how to restrict our curves or surface so that it is always increasing. It should not be here and there. Okay. So I just show you, yes, then smooth rational FIFs with shape parameters are well studied for shape preserving interpolation. Shape parameters help to preserve the shape inherent in data, and scaling factors provide fractality in suitable derivative. So means whatever techniques we have developed, our group or our lab has developed. So we are using these shape preserving techniques where shape parameters is there. You just fix the parameters, and you have this scaling factor. And in classical case, only shape parameters, no alpha. Okay, in fractal case you have alpha. So alpha ranges from -1 to 1, and again you generate infinitely many curves based on the desire of the industry or someone. Okay, then so what we try to do, we unify these two methodologies, means fractal interpolation function is in this direction and shape preservation in this direction, and we try to bridge the gap. So there are several problems like that. Someone is working on algebra, so he can see that where he can relate with fractal algebra. Okay, so someone is working on graph theory, then he can see some fractal nature of graphs or fractal theory. And someone is working like Atanu is working on harmonic analysis, so I ask him that we will bridge something on fractal plus harmonic analysis. So there are many things can be done, and means if you are working with your guide, the supervisor, then ask him to find such problems in the neighborhood of his or her research expertise, and try to bridge. Okay, so I just show you the figure, and this figure is here. So I have taken 4 points, and I just show you that I found the derivative of one interpolation. Okay, I have taken rational cubic spline fractal interpolation function, and I found the derivative, and you see the derivative is so irregular. Okay, and it is irregular though it is interpolating, right? And in that scheme I put alpha is equal to 0. Then I put alpha is equal to 0, then it is matching with the classical, means it is the derivative of classical spline. Okay, and it is smooth. So this paper I published in Applied Mathematics and Computation with my guide, and so I close this thing here, and I will go for the next presentation. So now we talk about some zipper or something. Okay. Okay, so we will start with, and I will invite sir after some time to help me in this. So we will go slowly because it contain lot of mathematics. Okay, so slowly we try to learn. Okay, so let script S is equal to S1 comma S2 dot 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 Sm be a system of injective contractions. So you know the meaning of injective mappings, right? You know the meaning of contractions also. Of a complete metric space, you know complete metric space also. A non-empty compact K subset of X is called the attractor of the system S if this happens. Okay, so we taught you already these things, means it is graph of F is union of transformed copies of itself, correct? So S1K union S2K union S3K union S4K, like that. Okay, and After doing all the unions you will get the K. So means K is the attractor of the system. We also call the subset K subset of X self similar with respect to S. Okay. In our case the maps Si belongs to S are supposed to be similarities and the set X to be R2. What is the meaning of similarities? I told you first day. D f of X comma f of Y is equal to R times D of X comma Y, and R must be between 0 and 1. And we use this notation I is equal to 1, 2, 3 up to M. In next slides we directly use I and K, something like that. So please write somewhere these notations, okay. That K is our attractor, okay. So after 10 slides, 12 slides K will come, okay. Then you just think that K is attractor, and meaning of K is equal to union of this one, okay. And I is the notation 1 to M, then is the set of indices, then I star is the means union of n vary from 1 to infinity I n is a set of all finite I tuples or multi indices, and J is equal to J1 J2 dot 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 Jn, and we write Sj. So this J is J1 J2 Jn, then Sj will become S J1 J2 Jn, and this meaning is Sj1 Sj2 dot 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 Sjn, okay. Means composition kind of thing apply. And for the set A subset of X we denote Sja, okay. So S1 S2 here, and you apply some A on that by Aj, okay. So we denote, means when we find Sj of A, that meaning Aj. We also denote by G script S is Sj such that J belongs to I star, the semi group generated by S. What is the meaning of semi group? Any algebraic structure with closure property and associative property, it is known as semi group, okay. So Gs is equal to Sj, J belongs to I star, the semi group generated by S. Then again I infinity, yesterday sir told this, no, I infinity. So this is alpha script is equal to alpha 1 alpha 2 dot dot, it is continuously going such that alpha belongs to I is the index space. So just remember I infinity, we directly use I infinity is equal to this kind of sequence alpha 1 alpha 2 dot dot dot, and pi is a map from I infinity to K, is the index map which sends. So pi is such that I infinity is containing points like this alpha, okay. So pi of alpha tilde will send to point this type of points, intersection of n vary from 1 to infinity, K of alpha 1 alpha 2 dot 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 alpha n, okay. So I just hold this slide for few seconds so that you can make the notations, you can write the notations, understand them, then we will go for the next slide. Done from everyone? Okay, so we go further. Now let X be a complete metric space. A system S is equal to S1 S2 dot 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 Sm of contraction mappings of X to itself, okay. X to itself is called a zipper with vertices Z0 comma Z1 dot 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 Zm, and like I was discussing fractal interpolation function, okay, there was no signature kind of thing, okay. Here they are introducing signature. So in signature epsilon is equal to epsilon 1 comma epsilon 2 dot 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 epsilon m, and each epsilon I belonging to 0 comma 1. If for any I is equal to 1 to m, and like in fractal interpolation function also we have two boundary conditions, right? ln of x naught, ln of end point, right? So here also you have two conditions, si z naught is equal to zi minus 1 plus epsilon I, and si zm is equal to zi minus epsilon I. And if you are interested in this work, then please download this paper written by Asif sir and Tetenov sir in the year 2003. Title is on self similar Jordan curves on the plane, and we try to provide you this slide today itself after the this break. And And whenever you want to understand this type of construction, then just take, means m value you fix 3 or 4, okay, correct? Like I have discussed fractal interpolation functions, so I was discussing all the things by taking 4 points, right? So here also you just fix Z0 to Z1, Z2, Z3, Z4 and try to think that what will be S1 Z0, what will be S2 Z0, what will be S1 ZM, what will be like that, okay? You just try to find.
We will practice it in
Tutorial.
IFS style.
Okay, so we will practice. Sir is promising that we will practice these things today in the IFS style. Now you see here, same thing. Okay, so we have 5 points: Z0, Z1, Z2, Z3, Z4, and these are mappings. And sir was telling yesterday that they are having signature 0, 0, 0, 0, and in the next figure it is 0, 0, 1, 0. So like I am changing the figure, right? You just be vigilant. So I am changing the figure. Now you see. Okay. So signature is reversed and the signature is 0, 0, 1, 0. Okay. So sir will teach you all these things, that how these things are working, and just he explained the figure by taking 5 points. So you also start visualizing by taking 3 or 4 points, okay? Then it will be easy for you. Okay? Then how to get this Levy curve? Okay?
Oh, no, this is a
Sierpinski gasket. So sir will tell the details, means how to construct this in IFS style. Do you have program for this?
yes.
Okay. So means
But this is the picture from Sierpinski work.
yes.
In his paper, there was such a picture without arrows.
Okay.
I did.
So sir is saying that here he put the arrow, but in Sierpinski paper there is no arrow, no directions, and
Signature is.
yes. So this point he is trying to match here, and this point he is trying to match here, right? And in the same way you can construct, right? And you make the iterations more, then you will get this picture and again this picture, right? Then if you will go indefinitely, then it will become Sierpinski triangular gasket, okay? Then there are some more theories there, means one theorem is there, how to find the structure parameterization of a zipper. So again we have taken S in the same way in previous slides, with vertices like I have shown you in the previous figure. These vertices are Z0, Z1, Z2, Z3, Z4. So we can go up to Zm and signature epsilon arrow. Then take some x0 less than x1 dot less than xm. Like in fractal interpolation also you have seen, no? We have always we have taken data points like in this way, and I don't know where we put the dusters here, right? Like we are thinking in this direction, like we take whatever data, okay? So we always take x1 less than x2 less than xn, right? Like this we take, okay? And suppose data is like this one, like a spiral kind of thing. Okay, so first data is here, second is here, third is here, fourth is here, fifth is here, like that, okay? Data is like moving, like a snake is moving, like, okay? So data is like here, means it is not single valued, these are multi-valued, okay? Clear? Our data is self-intersecting. Data is self-intersecting means it may start from here, it may go here, it may like data is like this one. Okay, so first point is here, second point is here, third point is here, then fourth point is here, then again like this. Okay, then how to interpolate those things. Okay, so this kind of work I have done in my thesis, chapter 8, means where I have taken data is not in this order. Okay, so I will send my thesis copy to everyone. Means if you want, then you can see those things. Means how did we interpolate it for multi-valued data. Okay, so there are many things, like Bansal sir has taken only this pattern. Okay, now suppose data is scattered anywhere, it can be scattered. Okay, so one student of Chand sir is, I think, working in this direction, and he started with some taking scattered data, and he is using some radial basis function things. Okay, so you can look their papers also, in that they are recently came in the literature, so you can see that how they are dealing with this type of scattered data. Okay, so ideas are similar, but we have to fix the technique so that it can work nicely. Okay, so here can we change this? We will ask him this question, that here also x naught less than x1 less than xm following some pattern, can we take irregular, can we take some scattered? No, there is no relation. Then what will happen? Be a partition of I is equal to 0 comma 1, and now script tau is t1 comma t2 dot dot tm, be a zipper with vertices x naught to xm and signature epsilon bar. So there exists a unique continuous map phi such that phi of xi is equal to zi, and this phi will commute with si. So in the next line you see si dot phi is equal to phi dot ti. Okay, so si dot phi is coming equal to phi dot ti. Okay, means the script s is having s1 s2 dot 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 sm. Okay, means one family of zipper, right? And this script t is having t1 t2 dot dot tm, another kind of zipper, right? And there must exist a unique continuous mapping phi such that si into phi is equal to phi into ti, and moreover the map phi is Holder continuous. Okay, so who will tell what is the definition of Holder continuous? A mapping phi is Holder continuous. When it will be Holder continuous? Phi, modulus of phi of x minus phi of y less than some c times into modulus of x minus y whole power alpha, and that alpha is known as Holder exponent. Holder exponent is alpha, and c, that constant, is known as Holder constant. Okay, so that you know. I can write here, means phi of x minus phi of y is less than equal to c times modulus of x minus y whole power alpha, and this alpha is Holder exponent, and this c is Holder constant. Okay, and what will happen when alpha become 1? When alpha become 1, then it will become, in the next we are using ellipsis. Okay, so when alpha will become 1, then condition will become ellipsis continuous. So next theorem is let s is equal to s1 s2 dot 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 sm be a zipper in R to power n, and suppose all si are similarities, and let phi the same mapping be the linear parameterization of s by a zipper, that t. So the Holder exponent alpha of the map phi satisfied, means you can always find the value of alpha by calculating this last line. In this slide, alpha is equal to minimum of log of lip si divided by log of lip ti. Okay, so by that you can find that Holder exponent alpha value you can find. Now what is Jordan arc criterion? Okay, like you know Cauchy criterion, right? We studied in BSc, MSc. So here also one Jordan arc criterion. So let S, again the same thing, S1 S2 dot dot Sm be a zipper with vertices x0 x1 dot 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 xm, in a complete metric space X row such that all contractions Sj such that X to X are injective, and if for any I comma j belongs to I, the set that, like in the previous first slide also we discussed about KIS intersection KJS, is empty. When it will be empty? For modulus of I minus j greater than 1, and it will be a singleton set for modulus of I minus j is equal to 1. Then every structural parameterization, that phi we are talking about in previous slide also, that phi from 0 1 to Ks is a homeomorphism. What do you mean by homeomorphism? In my lecture, first lecture I told you phi must be continuous, phi must be bijective, and inverse function will also be continuous. So this phi will be a homomorphism, and Ks is a Jordan arc with endpoints x0 and xn. Okay, so we try to provide, means where we have taken these theorems, we try to provide those references. Means I just asked sir to, after lunch we can sit and provide those notes. Then lemma and disjoint periodic arcs. Now suppose that Jordan arcs gamma 1 and gamma 1 in C with the common endpoints 0 and endpoints A1 and A2 are disjoint in C minus 0, and if the similarities Sjz is equal to Czz with modulus of Cj is equal to Qj less than 1 are such that in this way, then we were talking about here, right, this alpha, we talking about this alpha. Okay, so there will be alpha 1, so like that we will find alpha 1 and we can find alpha 2. Okay, and similarly we can find log q1 and log q2. So if both these things will be equal, alpha 1 divided by log q1 is equal to alpha 2 divided by log q2, where alpha is the increment of the argument of z along the arc gamma j dash, subset of gamma j with endpoints aj and sjaj in the direction from aj to sjaj. So here sir, I think we plotted this figure yesterday, right? So you know this, what is the name of this curve? Okay, and here means we have taken logarithmic of previous figure. This figure is there. Okay, and in the next slide we have taken logarithmic of this figure, and logarithmic of figure, and we zoomed the figure and some part of the figure we capture here. Okay, so you can see that they are periodic, in nature. Now sir told me to skip this slide. This is not relevant to our lecture, and now we are going to discuss about multi-zipper. Like yesterday I think we plotted zippers, and today in session we will see how to see the multi-zippers and dendrites. So now the definition of the multi-zipper is take skip z is equal to Fe and E belongs to capital E, be such digraph system of similarities with structural graph gamma is equal to V comma E. V means vertices and E means edges, and in each space I can go a little further, and you see here diagrams are here, you can see. So these are 4 points, and here also 4 points, here also 4 points. Okay, so now these whole 4 points, okay, how to see this figure, okay, how to understand this figure, these full 4 points by this map they are mapping to this interval here. Okay, clear? Means whenever this type of arrow is there, that means these all 4 points are mapping to here. Okay, and like it is clear again, this all the 4 points are mapping to here, this is also here. Okay, and like this full here, so you can relate. Okay, so sir will demonstrate more in this direction. So what is the definition of multi-zipper? So in each space xu, u belongs to v, v means this set of vertices, we have a finite chain of points z0 u dot 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 zmu u. Okay, then there is a bijection epsilon of the set of pairs u comma I, u belongs to V, and to E for any edge E is equal to epsilon u comma I, and efficients to like this way. Okay, so we will discuss this in detail after some time. And again the same thing here, means in previous slide this graph was there, and here you see that there is a line here, this kind of line, and this is which curve? Who will tell? What is the name of this curve? Van Gogh curve? Huh? Okay, so now you see in the next slides we are trying to make the multijipper. Okay, so this copy is here, this copy is here up to this part. Okay, you are able to see this is Van Gogh curve, and this side also the copy of Van Gogh curve, and this line you just see up to here, from here to here line, see, you are able to see, and the line, this line up to here. So this part is the joining up to lines, clear? And this side and this side, they are the copies of the Van Gogh curves. Okay, in the same way here you see the line, just the up line you just turn it back like that, reverse, and this copy is the copy of the Van Gogh curve. Okay, then you see here, so these are the multijippers. Very exciting figures, means sir showed me these figures in 2013. I think you visited IIT Madras. After Kerala conference, you came to IIT Madras first time, right? Then he showed these figures for multijippers. So very nice. So we will see, sir will show you these things in more details. And there are some more theorems or results, so I just read them, and so that we can become familiar with them. So let S be a regular graph directed system of similarities in RD means d-dimensional, R means R into R something, with Jordan attractor gamma arrow. If one of the components gamma u of the attractor gamma bar is different from a straight line segment, then there is a multijipper. Means when can you say that there is a multijipper? Okay, so this statement of theorem must be true such that the set of the components of the attractor object contains each of the arcs gamma u. So there is a proposition: if a Jordan arc in plane is a component of attractor of a multijipper, it satisfies OSC. OSC means open set condition. What was open set condition? So some of you know exactly what is open set conditions. Okay, okay, then we go further. So maybe from these slides sir can explain more nicely. Sir, you want to explain from these slides, because your part these figures will come here, so you can relate these things more nicely. Then I invite sir, please sir come. So he was explaining this figure. It will be 1 hour now. You have to teach for 1 hour. Break will be at 1.
At 1. So we have 1 hour.
Yes. Yes.
And I will make a GIAN now. Right?
Yes.
Tutorial.
You can explain these 1 or 2 slides, then you can go for tutorial.
Yes, because I need to return back
Okay.
and prepare some. And we'll make some pictures.
Okay. It is good.
Yes, excellent. 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 Okay. So, what we have to do? So we will begin with the definition of a zipper, and we'll try to
construct some. So does it work? Do you hear me? Ah, now you hear me. Okay. What is this? What happens? Do you understand this sound?
Yeah, this is, I think my WhatsApp is better.
Your battery?
No, I just
Okay, so I think we need to toggle laptops.
Okay.
Okay.
You want to use your laptop or this one you?
Yes, it is better if I use my laptop. Okay. And because you will feel very lonely without your laptop. I cannot allow myself to make you suffer so much. So meanwhile, I am preparing my laptop. We will try to look at the definition of a zipper in practice. So maybe even having this laptop unconnected, I can explain it a little. Yes. It says no signal. Okay. Yes. I have this. I have this one. Oh, no. There are many presentations, all very nice, but we need to have this one, I suppose. No, sorry. Just 1 second. This should be okay. Do you recognize what is shown on these slides? Yes. Very interesting. Why? How to make it single page. I wrote single page. Continuous plus. File. Who knows how to manage this problem? Yes. Line and which programs? Oh no, this is shown in Tech Shop. I will find it. Thank you. Okay. I just need to find this. Yes, in 1 second I will find it on my laptop, and after that I will switch, because it is absolutely impossible to distinguish super minimized letters. Curved, okay. I think, right? Yes. So this is a very old does it? It should connect. This is very wise. Oh, okay. So this is the definition of a zipper, and I think we need to look at it in more detail, right? So, as you remember, the first two zippers which appeared in mathematical life were von Koch and Sierpinski gasket. They were projected just in the way how we define a zipper. So it means we have a sequence of points Z0, Z1, Z2, Z3, Z4. Of course, if I try to be more economical, I can use just 3 points for von Koch curve, but I will do it in the next step. And then I draw arrows between these points. These arrows show the signature of a zipper. This is a signature. So this will mean that the signature is 0, 0, 0, 0. So zipper is a scheme which shows how we organize the similarities in a system. So it means that so we have similarities S1, S2, S3, and S4, yes? And S1 is designed in such a way that 0 goes to Z0 and 1 goes to Z1. Well, I mean Z0 goes to Z0 and Z4 goes to Z1. So initial point and end point are mapped by similarity to two consequent points in this sequence. Yes? The same way S2 sends Z0 to Z1 and Z4 to Z2, etc., 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 etc. Yes? So this is how the zipper with signature 000 looks like. And if we apply this map at first iteration, we'll get the figure. The figure which I try to draw in maximally identical to what appears on your laptop. Okay, so, and suppose we change signature from 0 to 1. It means, for example, let this signature was 0, and suppose we change this signature to 1. It means that instead of Z0 being sent to Z1, it will be sent to Z2, and Z4 will be sent to Z1. Okay. So what happens with this picture? Yes. it will turn upside down. Yes, it will turn upside down. So, so how do you think? Maybe we'll make some programming. Yes, because we need to check how it works. We can toggle signatures. We will fix for these 5 points. Yes. So let us write a program for IFS style. Since these points may be quite different, we will write it in the following manner. I define that 0 is 0, that 1 is, say, 1/3. Yes, that 2 is 1/2 plus 3 to the power 0.5 divided by 6. By 6, yes, by 6. Z3 will be 2/3, and that 4 will be 1. This is not the unique way. I can define these points anyhow. And now we'll define maps. So we will write S1 will be, you remember we defined the similarities sending pairs of points. Therefore S1 will be SIM 0, 0, 1/3, 0. Right? You have some objections? Objections, questions? No? Is everything okay? Can we continue? Okay. And S2 will be S2 will be SIM so what you have 1/3 0 1/3 0 yes, not very good. This is not very good because yes, it's better if we do this way, but maybe simplify, but for simplification we need to draw some additional procedures. Yes, Z2, this will be 1. Okay, so yes. So if it will be right, this way. Okay. Okay. Let it be so. Yes. 3.5 to the power 0.5 divided by 6, and S3 will be SIM. So it's a very awkward construction, but it will be good for us to toggle these numbers and changing the signature. Yes, therefore let us make this unpleasant work for one moment, and after that we will we will make it in a different way. Okay, and then it will be 1 half 3.5 divided by 6. Yes, of course we can denote this value by some letter, and then just put this letter here. So, this variable, and we have two thirds 0. Finally, S4 will be 2 thirds 0, 0, 1, 0. Okay, or S4 will be SIM of this. You see, so we have proved then, and then we write K equals S1, S1, S2, S3, S4 multiplied by K and see the result. How do you think? Can you do that? Did you do that? You will get the von Kochkev, please. Please. Enjoy.
So you are taking the signature corresponding to S2 is 0.
All signatures are 0, but then we toggle them from 0 to 1, and we'll look what does the signature make with this object. This object is very good because the similarities at the endpoints are homotheties. Yes. So no matter which signature we have, these endpoints will connect faithfully without infinite self-intersections. But when we change slightly, for example, the points Z1, yes, if we change Z1 slightly, then we'll get some unpleasant consequences. Yes, and we'll do that maybe we'll do that on some 3-point examples. Yes. So first we make it very simple. What?
There is an error showing when we put V1 as 1 by 3, 0, it is showing an error.
1 dimension 2, 1 divided by 3, 0. Let me look at it. At Z1 is 1/3 0. Okay. Z0 is Z1. G4, N is zipper, lower dimension is 2, Z0 is 0, Z1, Z0 is, Z0 is 0, 0, let me change it slightly, maybe it will work. Z1 is 1/3. Really, we don't need these 4 points. yes, these points are not, yes, no, right, you make comments, yes, sorry. So we need just these maps. This stuff is needed for reference, but not for the program. So K is S1, S2, S3, S4. Now it works, yes? Yes. this. So you will get von Koch curve without any problems. It will look the way it should look.
Just close.
No.
Just closed. Maybe I have to run it again.
Okay.
This is some other file.
And did you?
Showed completed and it just closed.
Oh,
I'll do it again.
okay. But yes, of course, because it's better to begin in some text editor, and after that yes. So it's sufficient if you write this in a text editor. Write this and this in a text editor. Yes. But since we need to see how signature work, we need these 4 maps because we can make variations. Okay? Okay, everything is okay. Yes. So everyone, yes. So very hard work of typing. Typing is not the best part of our practice. So you had the possibility to do something on your okay. Oh, you are. Did you make anything? Yesterday you made. We just need to this S1, S2, S3, S4, and then we'll toggle the numbers in S2 and change. See what changes happen when we change the signature. What? Didn't you? Yes, of course. SIM should be in your. You can copy it from some other place and put inside. Because it was defined yesterday. Yes? Okay, so then this is a zipper of signature 000, yes? To make it the signature, for example, 0100, you need to toggle these pairs. Yes, if you change the order of these coordinates, yes, then you will get a zipper of a signature 0100. Did you toggle?
Yes, sir, we are doing that.
Mm-hmm.
1/2 तो आएगा ना पहले point.
Really, you need not, you see, really you need not make changes. Yeah, you just write, for example, you can write S2A, yes, S2A will be SIM, and you toggle 1, 2, 3.5 divided by 6, 1/3 0. Better is okay. So did you make this turn? Yes, you see. Now you see what the signature means for our zippers. Yes, it makes such a rotation, and if, for example, we change this signature too, then it will be a very interesting result. Yes? If you toggle these coordinates here, yes, if you make S3A will be this one, 0, 1/2, 3 multiply 3 to the 0.5 divided by 6, yes? Then you'll get one more result. Yes, if you change S3 in the reverse order, then you will get one more result. Okay. Did you get? Oh, you have.
The program for same operator.
So all these things were made in your text editor, yes? So if you jump to your text editor and then manipulate with your text, and then after that you return to IFS style. Or otherwise, there is other way if, no. Of course, you can make in this editor, but it's better if you work with text editor. It's more simple. So what? Yes. 1 second. Yes, you have, but you need this program. Yes. And did you make it yesterday? Yes. So just open a text editor. Yes. And in your text editor there is a program. Yes. And you can just add this block to this program, and therefore it will use previous programs after the block is added. Yes. Yes, you can. Yes, you. The source is so you have this Koch curve AIFS. Yes, and you can jump. No. So you. I don't remember how in Windows you can change the program. Sorry. You can jump to some text editors. Yes, and you open this file in Notepad and make additions in Notepad. So Koch curve IFS. Yes, you have this. You need to open it in the Notepad. No. Open with. Yes. No. You have a Notepad. Yes. Do you have a Notepad? Oh, yes. And file. Open. And where are your IFS style files here? No. It doesn't see it. Yes, because you need to have all files. So you have just one, and when are the others? I don't know.
This is the recent one. This KKKK that I have just written that one.
Yes, yes. So they are, where are they?
This is showing error.
No. You need to open it with a notepad. Yes.
Open
Yeah.
notepad.
Yes. Maybe this way. You see, I didn't work in Windows for many years. I have open with, yes. Notepad, right? Okay. And this is a new one. Yes. And whereas you need also.
I just have to compile all.
Yes. You need to combine these files in Notepad. You just add this block in previous program.
5 by 6 is the mixed fraction. 5 by 6.
3 to the power 0.5 to the power. 3 to the power 5. Any questions? Sorry, my explanation was not good.
Sir,
No.
able to get that. My point is actually, sir, how are you getting this? This is from the zipper sequence.
What you ask?
So this one.
Yes.
What it is doing?
But we defined this subprogram yesterday. Yes, it sends the interval 0, 1 to the interval 0, 0, 1, 0. Yes. In our case, it's just a contraction. So really you can write that this is 1/3.
1/3 of it.
Yes, just 1/3. But and this is not 1/3. It's a translation by 1/3 0 and rotation by vector similarity, which sends 1 to 1/6. Yes. To this difference, 1/6 square root of 3 divided by 6. Yes.
So from that program,
Yes. Yeah. Okay. So this is okay, but what is the next? So okay, it works. And now you make. You add. Excuse me. Instead of XP, enter. Yes. You make S3A. Yes. And you have this SIM, but you toggled first two values with second two values. Yeah. And then replace S3 by S3A. Yes. Yes. Okay, so you
shifted the coordinates for S2. So one side you can have.
Yes, I see. Yes, really, it's so. And can you do the same with this S3? S3. Okay. Oh yes. Looks wonderful. Right. Yeah. Yes. Yeah, we changed two signatures, and it gives us the result. Please. Okay. Right? I hear you.
We need to copy these things.
Sorry. Excuse me. What it is?
On that previous yesterday's.
Yes. This SIM.
And another was it was that.
Yes. But you see. But you have only this file, or can you? Yes. And you have test here, right? And since SIM is here, you can add something to your test. For example, or you can add block. Yes, so this is, so you can just print. So you can just print S1, S2, S3, S4 here, and write L, change different letter for the attractor. Yes, it's okay. So, and if you toggle both, then you will have oh yes. Okay, so now you see how signature works. Okay. Did everyone see how signature works? Yes? Okay. Okay, Vijay. What?
What is the problem now? Everything in the block.
Everything. Yes, and it doesn't show.
No, nothing.
Apply. Yes. SA1, SA2, SA4, KA is KA. Yes. And you said apply, but you have this.
That I don't know how it can. You can check. Yeah.
I don't understand. Why is it? And let me check here. No, it doesn't show. This is this one. Maybe I understand. So let us make some will it work? Fantastic. I don't know what happens, but it began to work. So, do you have some problems? Battery, yes. There is a... yes? Oh, fantastic. It looks very nice. So you see what is the signature of a zipper. It's a very important question. Okay, so if you have made a picture with a zipper and signature, let us turn to basics, because we have too many points, and as Professor Saurabh Katiyar told, we must begin with 3 or 4 points instead of these 5. So let us do the following things. So you create a new block or create some new lines in your program and define the following things. So we take 3 points, 0, 0, 1, 0, and AB, right? Okay? We create such 3 points. How we will create? So you have first you need to define AB. What we'll do? We will construct 4 zippers, because we have signature 0, 0, a second will be signature 1, 0, yes, 1, 1, 0, third will have a signature 0, 1, and fourth will have a signature 1, 1. With the same coordinates, it will be 0, this will AB, this will be 0, this will be AB, this will be 0, and this will be AB also. So we will take four such objects. They will be called maybe K1, K2, K3, K4. Yes? So what it will be? It will mean that first we need to define A and B. Suppose these points A and B AB are the points AB runs through this square rectangle. Yes. So I write A. I define as A as some random real number. So I write, first I write that this is a number. Yes, and in the parentheses I write that it is real. And it changed from 0 to 1. Or if you wish, it can change from in some smaller extent. Okay, real. Oh, sorry. I forgot what kind of parentheses are here. Round. Okay. Okay, round. Yes, round. Because brackets are for vectors, operators, and other stuff, and matrices. So it will be 0, 1. Okay. And as far as B is concerned, we will make it a little smaller by so A, B will be also number, real, and it will change between 0. Or if you wish, you can allow it to change between minus 0.5 to 0.5. Yes. Okay, so let us write this way, minus 0.5 plus 0.5. Okay, we have written these comments, so we have a freedom of maneuver. We can regulate these values in these domains, right? And now what I do, I will write K00, yes, it will be SIM of 0, 0, A, B, union let me write it in different way. For example, let S10 will be SIM 00 AB. S11 will be SIM AB 00. S20 will be SIM AB 10. Yes, and S21 will be SIM 10AB. Okay. We defined this two variations of first map and two variations of second map. And now we write K00 is S10 union S20 multiplied by K00, right? K10 will be S11 union S20 multiplied by K10, right? The same with the K0, K01, yes. K10 will be S1 S11 union S20 S. Yes. 1 second. Signature 0 is S10. This is S21. Oh no. K0. Yes, S21. Yes. 1 0 1 1 2 0 is okay, and this K10 it will be S11 S20, and K11 will be S11 S21, and you multiply it by K, it will be K01, it will be K10, it will be K11. So if you do this, then in your list of constructed objects will be these 4 objects. But the problem is that we need to compare them. So to compare them, we need to place it at some safe distance from each other. Okay. Therefore, I write some good letters. All. It will be all. It will be. So I take K00. So I will place them in a table this way. You see? I will place in 4 boxes of a table. I don't draw boxes, but just place them. So so this will be, point will be 0 0. This point will be, say, 3 0. This point will be, say, 0 2, and this point maybe will be 3 2. Yes. So I write all is K00 union. Then I shift by 0 to the set K01. Yes, K01 will be here. Then I will shift by 3 0 the set K10, and then I shift by the distance 3 2 the set K11. 1 0, it will 1 0, and this will be 1 1. Okay, so please do this, and you will be able to compare all these 4 zippers in one picture. They will not intersect because I made sufficiently large distance, and you will be able to change the parameters. But first you need to draw all these letters. So you have a problem with your laptop now? What it is? KF. Okay, it's good. KF is. It's really so. Yes, you're right. And you suppose that you will have 4 von Koch curves? No. You fractals are weird. If you... You're doing, yes. I wish you success in your doing. What? Error. Oh, yes. It's a problem. The teaching programming techniques is a constant fight with errors. Yes. They appear from the line and block. What is the... sorry. I don't see the file. Where it is? So, okay. So you opened IFS style? Right. Why it looks so strange? Where is open file? SIM IFS? Yes, I open, okay. And it doesn't, yes, it doesn't want to open. Can we open a notepad?
Yeah, it is here.
It is here, yes, okay. Let us look. SIM. Oh, you have, you just defined two subprograms, but you have no program. Let us make it first. Maybe it will be some program. It has name. You need to define a dimension. A dimension. Oh, thank you. I suppose you need 7, but if you choose 2, it's good. Yes, then you save it, right? Control S, right? See? And then try to open it again. File, no, file. Open. Okay, yes. Open. Oh, yes, I see. KA, KB, KC minus KA. That again. Continue. Return. KA, KB, KC, KA. Very interesting. Return key. Everything is defined, but KA0, KA, KB multiplied, KC, KB minus KC minus KC minus K. So everything is okay. Let me check some.
So here I have to define it as sim dot.
Yes.
IFS like that.
No, sim SIM2.
Sim2.
Change name. Point IFS. Yes.
Okay, now we can open it.
And the same problem. The same problem. Can I? Where it is?
Just check that it is saved or not. It is here, no?
Yes.
This file is here.
But what is the extension?
It is like this one.
Extension txt.
.txt.
You need .ifs.
How I have to change?
You change the extension. Save as, and change the extension.
File.
Save as.
Yeah, this file I want to change.
Yes. But you need to change the extension. Yes, this Windows do not show extensions.
Okay. So I directly write sim.aifs.
Yes, and not text documents, all documents, all files. Yes, okay. Save. Yes. Let me check if it exists.
Yeah, I don't want this file. Now we can open sim2. File, open. There are unsafe changes. Okay. Sim2. Okay. This one, how to open now?
I see nothing. Okay.
The file does not exist.
Yes, very strange. It's a problem of Windows, but this problem is everywhere. Can you?
IFS style.
It's in this.
IFS style last one.
File Explorer, right? Sim2. It is IFS. Yes, line and block, line and file, line and block 6, line and file 8. KC. So here we have maybe it's better if somebody sends you good file because we can enjoy this improving mistakes in. Can you share your file with him?
Yes, sir.
Huh?
I said.
Okay. Okay, so did you make these 4 objects? They are too large? No. But where is the 4 objects? I asked.
No.
Oh, but you need all.
Yes, sir, also I applied.
Yes? Where is all? No, just all equals K00 and K10, and there is a very small mistake. Oh, sorry. Oh, yes. Star, please, star. Okay.
Now
Apply, yes, look. Look at the list of all possible objects. Here. Oh, you see all? There are 4 objects, yes? And now, no, don't. Now you go here, here. Sorry. Controls.
Yeah, I can change that.
Okay, and did you?
I didn't get in 4.
Oh, what you didn't get?
I didn't get in 4.
Let me look at your. So you have this one key. Oh,
Okay.
yes, everything is okay. Now you can change the parameters and see how the zippers act when you change A and B. Yes. So did you make them all? Where are?
There is something.
Wow.
But only 3 are there.
It's very interesting. Can we? So SC2, SCD, SC1, SC2 multiplied by KC. Is there any kind of a mistake? No mistakes. A00. SIM works well, but why these objects are not working? So KC, KD, KC, KD, KE, KF, KC, yes, KD, KE, KF. Can I look at them separately? Oh, KC. KC n'existe pas. Yes, why it is a point? Let us.
We take a random A and B.
A from 0 to 1, B from minus 0.5 is, and SC1, SD1, SC1, SC2, so KC SC1 and SD1. Yes? Yes, because you had 2 operators with the same fixed point. If you have a system of contraction which have the same fixed point, then the attractor will be this fixed point. It's fantastic. Oh, and now you change parameters. Here everything is okay, but where to find how to change the parameters? You see, no, not this way. There are controls, and you begin to vary them. It's changing of A, and it's changing of B. Okay, but 3 was too much. This 3, maybe 2 will be enough. Yes. Do you know how to change the parameters? Okay. I would like to show you how can you change the parameters, because it is very simple, but it must be shown. So, for example, I need to open some program with parameters. So when you press on this button, editor, yes? Look here, please. Do you see my screen? Yes? So you press the editor, yes, and editor has several options. Here you see the source, yes, but if you press this arrow, you will have some other things. Controls, yes. When you press controls, then you will see the controls for A and B. Unfortunately, I was lazy. I didn't print this program, so I cannot control A and B because they are not defined in my program. But in here, and then you will see A and B here, and you can slide them by your finger. Or okay, you understand it? Control? No. Where? But where you have A and B? Oh, you have you can change, but I don't see them. You have only from Korkev. Yes, okay. A and B. Yeah, it's alive. It's alive, yes. Okay, so did you know how to control change A and B? Everyone understood. So you can make some leaf pictures in fractals, and just changing parameters you can see how to make very good one among them. But what must be shown, let me find some RFS style program with zippers. Open files. Escape. Open. Levy curve. Sets. Maybe this. What it is? No. I have no such program at hand. I'm at. Okay. Oh yes, I have this one. I have this one. For example, I have a zipper on 4 point, and here I have 2 parameters. Is it visible? Is it okay? Yes, I have 2 parameters, and I can change these parameters. So in this picture I have shown the arrows showing the signature, yes, and the result. Yes, so this is a zipper with the signature 101, right? And I can change the parameters. This zipper is very good because it has alternate signature. Yes, therefore at each point the endpoints of the same time meet. Therefore there are no intersections. But if we change the signature, then we'll get much worse result. Let me check if it yes, this is also alternate signature, and what is about this one? And this is, yes, I have 1 0 1 0, and this is also 1 0 1. Yes. If I change the signature, then it will be 1 second source. Source. Yes. So what happens if you have some kind of an endpoint in a zipper curve? Yes, yes, yes. Let us have a lunch. Yes. Then we can start. So the lunch break is. I have not taken my schedule. Today is On, okay. Yes, it will be a lecture supported by computer simulations made independently by the listeners. Yes. So it is a lecture. Yes. 1 second. I need to. For that lecture, I need to open the open a presentation, and it is here. 1 second. I need to look at my screen. My screen needs magnification. Let me check if, no, this not. Oh, yes. No, I will switch it off. Because when I switch it on, I cannot see the letters. I need a microscope. And you did not provide me a microscope, so I need to switch it on. So we return to the slides which were explained a little by Professor Katyar. Right? 1 second. Yes. What happens? Okay. It works. So we looked at zippers. Yes. Considered how to build zippers of different signature, right? And one very important fact that zipper creates a curve, which is a Peano curve passing through the attractor of a zipper. Yes? Why? If we have a zipper, then we can parameterize it. We can make a natural parametrization, or it is a structural parameterization of a zipper. You see, suppose you have some kind of a zipper, for example, this one. Right? And we can make an elementary zipper, whose vertices are situated on a line. Yes? So it will be S1, S2, S3, and this will be T1, T2, T3. And we can make a, how to call it, a morphisms of two zippers, yes? So which will be compatible with this system and with this system too. So we have a map F, and this map is satisfies the following equation. F of Ti of x is equal to Ti or Si of f of x. So if I have a point and I have its image, right? And if I applied some maps, maybe T1, this point goes here to T1 of x, and the image of T1 of x will be S1 of f of x. So this mapping is easy to construct, because it's also this mapping may be considered as a special case of fractal interpolation functions. Yes, because it's a function with values in the plane. Yes, so it's and this equation is the same as the equation of fractal interpolation function. So when a point travels along this interval, its image will travel along the attractor of this zipper. So it will be a piano curve running through the attractor. It will be a piano curve running through the attractor. So when Sierpinski, does it work? Oh. When Sierpinski projected his Sierpinski carpet or Sierpinski gasket, so he made such a piano curve. What? And his intention was to make a curve which has double points everywhere. You see that this branch of this curve and this branch so meet at that point, and this meeting point repeats everywhere. So the name of this paper, an example of a curve which has ramification point everywhere. Okay. So zippers, but you would ask me, why the attractor of a zipper is connected. But you see the zipper has one intersection property. Yes, because each copy of a zipper has a non-empty intersection with the next copy. Therefore, the intersection graph is connected. And if intersection graph is connected, the attractor is too connected. Yes. So zippers are just self-similar curves, which may have double points. Okay. And this map, which sends elementary zipper to this zipper, is called a structural parameterization. Structural parameterization of the zipper per K of S, where S is the system S, S1, S3, Sm minus 1. Yes. So when we consider the relation between the zipper and elementary zipper and its parameterization, then we see that it will be Hölder continuous. Yes. And its Hölder constant will be minimum of relation between logarithm of Qi and logarithm of coefficients for Ti. Yes. In that sense, it is better to make these contraction ratios similar to each other. Yes, in that case, the ratios of logarithms will be the same, and it will give us the same Hölder constant everywhere. Okay. So what is interesting is how to recognize when the attractor of a zipper is a Jordan arc. Yes? You saw that some attractors are Jordan arcs and some are not. What happens? So if the attractor of a zipper is a Jordan arc, then its copies do not intersect, with the only exclusion that they intersect at their common endpoints. Yes? And again, if the copy intersect only at these common endpoints, then the attractor of a zipper will be a Jordan arc. So here is the theorem. Suppose we have a zipper with vertices x0, m. No matter in which metric space it is. You have questions? Yes, I welcome all the questions. If there are no questions, it is not good. And if for any ij, so it will have several copies, ki, kj. So if I and j, if j minus I is more than 1, then this copy do not intersect. And at the same time, if j is equal to I plus 1, they should intersect in a unique point, which is the common endpoint of these two copies. And in this case, the structural parameterization will be a homeomorphism between a line and a Jordan arc. Will be homeomorphism between a line and a Jordan arc. So there are two cases when these two zippers are Jordan. So when we consider this, so you have a zipper and you have a common endpoint of two arcs. So this will be S1 of gamma, and this will be S2 of gamma. S2 of gamma. And this will be 0 and 1. So there are two cases. If you have here, for example, S1 of 1 is equal to S2 of 1, then we have two similar arcs, yes? And one arc is obtained from the other by some kind of a similarity, yes? And these arcs act as loxodromes. They are spirals, yes? So if you have two spirals, they can meet each other in two ways. First, if the angles of inclinations of spirals are the same, yes, then they will have one point in intersection. But if the angles of inclinations of two spirals are different, then they will intersect each other in infinite number of points. In this case, it is good to look at this situation from the point of complex analysis. So in complex analysis, if you have S of Z equal to Q e to the power I alpha Z, yes, then, so if you take some points and you consider the images S to the power of n of some initial point Z0, yes, Z0, then this point will lie on a logarithmic spiral, yes? But in reality, the curve is different, yes? Yes. But if we take a logarithmic transformation to this picture, then this curve is transformed to a, so you know that logarithm is a multivariate function, and its values differ by 2k pi. Yes. So if I take the logarithm of z0, then I will get logarithm z0, logarithm z0, z0 plus 2 pi, 2i pi, yes. Then we'll have logarithm z0 plus 4 I pi, etc. Yes, we'll get a sequence, infinite sequence of these values. And if I take a logarithm of q e to the power a alpha of z0, then I will get, so let us take this logarithm. Logarithm of q e to the power of a alpha z0, it will be equal to logarithm q, right, plus I alpha plus logarithm z0, yes? So this similarity transformation, after taking a logarithm, becomes a translation, right? It will be a translation of the whole plane. So when we take this logarithm, this point is translated, it will be z logarithm z0 plus logarithm q plus I alpha. And there will be an arc connecting these 2 points. And instead of having one arc, we'll have a family of parallel arcs, right? Oh, sorry, don't you feel tired of complex analysis? Is it good that I explain to you these things? I need a feedback. If you may be dissatisfied or you have some questions, then please ask me your questions. Okay? And if we repeat this S, then we'll get the parallel copy of this arc, and we'll get a family of parallel curves. Right? A family of parallel curves which are invariant with respect to this translation. Plus logarithm q plus I alpha. Yes? Logarithm, since q is less than 1, this is translation to the left. Yes, but I alpha can be quite different. Yes, so this will be parallel lines. But we have a meeting point of two copies, yes? And for the second copy we have another transformation. So this is a logarithm q1 plus a alpha, q1 plus a alpha, and the other will be plus logarithm q2 plus a alpha 2, right? So we'll have another family of parallel periodic curves. But for these periodic curves, we can define the angle of the inclination, and angle will be the arctangent of logarithm alpha divided by logarithm q, right? Yes. And if these angle coefficients are equal, then we'll have a chance that these parallel lines do not intersect. But if the angles are different, they will intersect each other infinite number of times. Yes. So this picture can be seen on your zippers of signature 00 when you make some kind of an angle. Yes. So do you have such zippers on your pictures? So not so. Yes, but I need to see where is the meeting point of one copy and the other. So when you have signature 00, then you'll have such intersections of spirals at any. Yes, it is visible, but the problem is, so it is 0, it is 1, and this is point AB. It is somewhere, yes? Okay. Can you look at it? Did you look at your... no, this is signature 1. You need signature 00. Yes, signature 0. Yes, you see? Oh, very good picture. So you can magnify this part. You can magnify. Oh, not. Return back. Okay. And make some. I need you return back. Yes, this button. And then you have this meeting point. It is here, and make a symmetric rectangle about this point. Okay, that's good. So you see this. You see how these two spirals intersect each other infinite number of times. Yes. Yes. When yellow and white meet. So, and you have very good pictures. Because different, if a person is good, then his or her pictures are very good, and he cannot spoil it even he wants. You have this. Oh no, you have here some problems, some very special problems. But it is. You need to make you need to change the parameters A and B. Oh, sorry. So if you change the parameters A and B, whereas parameters again, source controls. Yes, controls. You see, they are very small. Let me make it greater. Sorry. A and B. Very strange. A must be 1/2. Something like 1/2. Okay. And B may be whatever you like. Maybe let's make it smaller. Yes, okay. And then you need to make it this way. And look at this picture. Oh. Yes, I cannot, so you need to, yes. So, 1 second, if you have one colored picture, please press the button rendering, view rendering. So there is a view, and then rendering, and yes, press depth. Change the depth. Then the copies will be view. Oh. So what happens? Yes. Okay.
Changes the depth.
No, but you need to see the attractor. Not, it is K00, yes. It's always a secret. What name? No, I mean, I don't mean that. I mean the parameters, controls. So A is good, but B, let us make B greater. Maybe we'll make B greater, and now we have these two spirals, but this, okay, let it be so. So we can look here. Oh, no, sorry. Tools, zoom box. Oh, tools. Okay. So there are spirals and spirals and spirals, yes? Okay, and what? Not working, it's a very special problem. Okay, so now you saw this infinite number of intersections, but in the case when these ratios are equal, then everything is okay. Now let us continue. So this is just a picture of this logarithmic transformation. There was a very good program called Fractracer, and I had a dream of applying it, which can apply different transformation to different fractals. I used it till 2013, but then IFS style appeared, which is faster, and also I changed from Windows to macOS, but Fractracer works on the Windows, so maybe we can discuss if you have Windows, and if you wish to install it, we may discuss this Fractracer program, because it makes what? The name. This program was built by the same person, by Dmitry Mikhontsev, Fractracer. But now I don't know. He had Maybe it can be available from fractracer.com, but he left it. He supposed that it can be used for building different landscapes for computer games, but this dream was not realized. But this fractracer, I could take a model, for example, Menger sponge, yes, and from this Menger sponges, I made a torus, and I could rotate the torus around this axis. So I have video of such Menger sponge. I can show you this picture. So it allowed to take a fractal and cut it by surface and made this surface cut of fractals. So it is very interesting. For example, I took Menger sponge and cut it by a ball. So I got Menger ball. So it looks so many unusual features of fractals can be uncovered using this program. But so we can make an attempt to install it, but I need Windows on my laptop, and this is not easy to realize. So when this zipper has alternate signatures, yes, then this parameter matching condition is satisfied automatically. So there is some domain of parameters for zippers with alternate signatures, yes, in which all the attractors are Jordan arcs. So this is very good. So when you look at the picture, when you have this one, then you have this one and this one, and change parameters, then you will discover that in this case almost all attractors are Jordan arcs. Almost all attractors are Jordan arcs. Yes, maybe I can show you the movie of the type if I succeed this. When we have a break, can you explain at which time we need to make a break? It's already break.
4 minutes. After 4 minutes we can.
After 4 minutes we make a break. Oh, that's very good. Then I will find you that nice picture which shows that Z all. Z. Oh, sorry, I to find everything I need to all. Okay, I will show you this picture after the break, and now I continue my talk. Where is it? It is here, I suppose. Okay. So the problem is, what is a multi-zipper? Multi-zipper is the same as the zipper, but if we have several polygonal lines, and we begin to map. So we have, for example, we have two attractors, K1 and K2, yes, and one is maybe is represented by such a zipper and such a polygonal line, and this is represented maybe by that polygonal line, right? Yes. But we may, by some arbitrary choice, we may map K1 to K2 and K2 to K1. So this is a typical situation with graph-directed systems. Maybe to understand graph-directed system, you can, at first, you can construct the following very simple example. Consider a square and a triangle, yes? And let us suppose that this square consists of two squares and two triangles, right? And suppose this triangle consists of one square and also two triangles, maybe this way. You see? Is it possible to construct such a system? Is it possible to construct such a system? Of course it is possible, it is easy. So suppose this is 0, 0, this is 1, 1, this is 1/2, 0, this is 1, 0, this is 0, 0, 1/2, 0, 1, 0, right? And I need to write the maps, yes, which send first set to the first set in these three different ways, yes, and second set to the first set and second set in these different ways. So, and I write K1 is equal to, I will write it just as a comment in IFS style, yes? So it is 1 divided by 2 multiplied by K1, yes? And also union, this will be 1/2, 1/2. But since we have 1/2 both times, then it will be better to write this way. 1/2 multiplied by 2 copies. First is identical, and second is shifted by 1, 1. Right? Yes? Multiplied by K1. Please repeat your question.
Okay, sir.
Yes. So if I am wrong, please prove that I am wrong, and I will ask for. Will ask to forgive me, but at that moment I am right. Therefore, no problem. And now I need to add here 2 triangles. Yes, the first triangle is this. How to put? I need to rotate this triangle 90 degrees. Clockwise, yes, and then I need to shift it to this point 0, 1, right? and it must be contracted 2 times. You see? So let us write this transformation. I shift it by 0, 1. Oh, 0, 1. Yes? But before that, I contract it 1/2 by 1/2. Yes, 2 times smaller. And but before that, I have to rotate it. How to rotate it clockwise? What is the matrix of clockwise rotations by 90 degrees? So if you have a vector AB, if you rotate it here, then it will be B minus A. Yes? AB goes to B minus A. AB goes to B minus A. So the first coordinate goes to minus second. It will be a matrix. A goes to A goes here and B goes there, right? This is a matrix of rotation, of clockwise rotation. Let us check. When I was child, I could not distinguish between right and left. Yes? Therefore, I need to check. Is it a right rotation or left rotation? For example, if I take 1, 0, where it goes? 0 minus 1, so it looks there. Yes? Okay, so we rotate it clockwise. Okay, clockwise rotation is 0, 1, minus 1, 0. This is the first, and this is counterclockwise rotation with the translation by with the translation by 1, 0. Okay. So I will write it not economically, but 1, 0 multiplied by 1/2, and multiplied by 0 minus 1, 1, 0. Yes, this is a counterclockwise rotation, and this union is applied to K2. You see, and then we write K2. We need to express K2 in our terms. So it will be 1/2 multiplied by K1, right? We took K1 and shrinked it 2 times. And also we have 2 rotated triangles. Rotated, they are rotated at which angle? It is a... So initially it was here, and now it became here. It's 5 pi. So what is the matrix of this rotation? So first, I need to understand what is the... It is a... If it is 1, this is 1/2, and this is square root divided by 2. No, square root of 2 divided by 4. Square root of 2 divided by 4, right? Square root of 2 divided by 4, it works for those both two. And 1 second. First, we need to find coordinates of these 2 points. These coordinates of these 2 points are 1/4, and it will be 3/4. Yes, So I write the coordinates of the vertex, 1/4, 3/4, yes. Then I multiply it by a rotation by how much? 1, 2, 3, 4, 5 pi divided by 4. No. Oh no. How much? What is this angle? 3 pi divided by 4, right? 3 pi divided by 4. 3 pi divided by 4. And also I add a translation to this point. And this will be 3 divided by 4, 1 divided by 4. So it will be 3 divided by 4, 1 divided by 4. If somebody can and multiplied by rotation, which is this rotation? -3 divided by rotation by -3 pi divided by 4. Am I right? -3 pi divided by 4. And all these two components are shrinked square root of 2 by square root of 2 divided by 4. Square root. So it may be written as 2 to the power minus 1.5, yes? And this is K1, and here it will be, this is applied to K2. Do you see what is written on this part of the blackboard? Is it visible? It's okay? Okay. So now you will construct an attractor of a graph-directed system. Usually, construction is being blocked by some mistakes. On that way, you need to eliminate the mistakes, and then you will get the success. I think that we need to make a break. Yes, and after break, I will continue this explanation of graph-directed systems, because I need to explain multizippers.
So please sit. We can bring your tea.
Yes, I will be grateful, but I need to wash my hands. They are black.
Yes.
noise? Yes? Okay. If there is too much noise, please make this way and you will feel comfortable. I don't like the noise of this system because it transforms the voice to some kind of unpleasant sound. Okay, so I need to see the result of your efforts to build the graph-directed system. Simplest graph-directed system, because I can explain you graph-directed system 100 times, but when you make it with your own hands, you will understand it 100 times better. You can study fractals theoretically, but if you make them with your own hands, then you understand them because you feel them. So did you write these operators? Who needs help? Yeah. You need help in typing the program?
I'm typing up. Can I type that root 2 by 4? Can I write x to the power half by 4 now? Because root
2, yes, 2 to the power 1/2 divided by 1/4. I don't know what it must be. And it says any mistake?
yeah.
Let us check.
Apply.
Oh, sorry. Apply. Line in block 30. Oh, yes, 1/4. Yes, 1/4, 3/4. You have a. You need to have a bracket, but you have a.
Oh yeah, third one.
Yes. No one knows where the danger comes from. You suppose that you made some mistaken formula, but it was what?
2 to the power half by 4. That only coming.
Yes, because there is one more closing. One. It is closed, but it was not opened. Yes.
No, that is for that one. No.
And by what is multiplied by this operator? This
is for first one.
And no, 1/2 is applied to K1, but there is no K2. You see, you need to write star K2. Star K2, yes. K2. Let us check. Oh, again. Error at block. Escape. I will do one pretty thing. Okay. I just need to look at these letters. What is the reason for protesting? So this is 1/2. This is opening. This opens. Opens 1. Opens 2. Opens 1. Opens 2. Opens 1. Opens 2. Opens 1. Opens 2. Opens 1. Opens 0. Opens 0. Open. You see? Okay. So this is opens 0, opens 1, opens 0, opens -1. You have two two more closing parentheses, then it is needed. So you need to erase unnecessary parentheses. Counting parentheses, yes. Who needs help? Who needs assistance? Who can show me the result? Yes? And you have no laptop? Yes. It's not good from me. This is what? Very interesting. And K2. Yes. So can I read this editor? Because it should be analyzed. Sorry, I don't understand. No, you have macos, but why? Yes. Oh, not so much. Can you adapt the size so that I could see? No, this. User interface, it must be not that say. No, there is user interface and no, this is not the way. Tools. No, Zoom box, no. We have user interface settings, and they are under this button. Yes. So, can you save all the results, close the program, and open it again? Yes. Oh, very good. And the second one? There are two objects, right? Yes, okay. That's very good. And did you succeed in building this?
No, sir.
Why? Errors?
Yeah, maybe some small mistake with the parenthesis steps.
Yes, because I was counting parentheses in one person here, and he had two more closing parentheses than opening ones. And you are making tiles, yes. Constructing tiles and analyzing tiles is main. Yes. What is? This can I enlarge it a little? Maybe this way, okay? To see the magnified result. So you need to make parentheses here. 2 to the power 1/2. Yes, or please. 1/2 must be enclosed in parentheses, not square but round brackets. Absolutely. Absolutely correct. Check. Again, because there are many problems with them. In this, yes, it says that problem is in this line. 1/2 multiplied by k1, and there must be union sign, right? K1 is small, right? Okay. 1/4 3/4 multiplied by rotation by 3 pi divided by and you need to close. Not this all, but 3 pi divided by 4. No. 3 pi divided by 4. This all, yes. Okay. Union 3 4 divided by 4. Rotation.
This one bracket is more here.
Yes, I don't see anything of that sort. Okay, let's check. Oh. 1 divided by 1. Union. Open. 1/4 3/4 close. Rotation 3 pi divided by 4 closed. And this opens, and when it closes, this parenthesis closes this one. Yes.
But this parenthesis.
Yes, this parenthesis is not used. Okay, and to what do you apply all this stuff? So you don't apply, you just write some letters and it's okay. They are not applied to anything. They are good by themselves. Close the star K2. Check. Wow. Line in block 24, 1/2 K1. It's okay. 1/4 3/4. Rotation. Yes. So 1/4 3/4 multiplied by rotation. Close this. Close the parenthesis. Just in case. Yes. Just in case. Yes. And then open the parenthesis. And 3/4 1/4 rotation. And after rotation star. So no. Rotation, and then here you need to multiplication sign. Yes, 2 to the power divided by 4, and this. Oh, sorry. And where is the? You cannot open this one. Backspace. Sorry. No, return. Control Z. Yes, because I pressed wrong. You see, one. So K2 is this one union, this one union, this, and here you open the parenthesis. Oh no, sorry. Excuse me, please. Union, then you have this one, and there must be some kind of union between. Yes, but this union sign, this cannot be used there. Yes, 3 4 1 4. So this union is applied to K2, so this bracket is opening here. And this is opening there. So make this one and this one to enclose this all this. Oh, no, sorry. First you begin here, parenthesis, yes, and second you close there. All right. Now check. You didn't define pi. Pi equal to a sine of 1. Pi is 2 arcsines of 1, right? Here. Somewhere in the beginning. Here. Pi? No. Pi equal to 2 star a sine arcs sine, yes, of 1 no, of 1 in parentheses 1. Okay, apply, it works. You posed a lot of problems for me, yes. Very interesting. What is the problem? But it works.
No, this is not problem.
It doesn't say anything?
Yes.
Yes.
Not saying anything.
Yes. Doesn't say anything. First I need to... It's good, but not everything. Not all operators are listed.
K2 is coming, K1 is not coming, right?
K1 is not coming. So you need to look at K1. First you need to press this button and enlarge the picture. Enlarge it. Okay. And then enlarge this field. Okay. So K1 is not coming. K1 1/2 multiplied by K1 0 1/2 multiplied by K2.
Here multiplied by K2.
Yes, of course. If you have K2, then there must be K2. Star K2, okay. Okay, and K2 is 1 multiplied by K1.
That's for K2, that will be...
No, this is not needed here. It is not needed here, yes. And do you think it's so? You open it, and close here.
Yeah.
It's okay?
Yeah.
It's okay?
Yeah.
Apply? Do you have K1? K1 is here, but it is not completely... Some operators are missing, and operators are missing in... Because here you have K2, but here you need to have K1 in. Here you need to have K1. So when you define K2, this is 1/2 multiplied by K1 and other things multiplied by K2. But when I see the K2, something is wrong. This is K2? Yes, because in K2 there should be K1, yes? And in K1 And what's about K1? But why K1 is such? K1 is very strange, you see? It must be a square. So find your missing. Are you okay?
No, sir. I tried.
What?
But it's something.
Identify. Please.
Yeah, I
It-
find it.
You found it, yes. What?
Getting this type of fractals. So it is
You are not getting or getting?
getting it. This type of.
Yes.
Is it true or not?
Yes, it's true. Of course. Everything is okay. Yes.
If we, so what is the rule of these values?
And these values are coordinates of these points. We have these 2 points are fixed, and this point change the position. So
We can put any number over here.
you can put no, you can put very large numbers because there will be no contractions. Because this value must be, its modulus must be cannot exceed 1. It must be less than 1, yes. So if you have no contraction mappings, then you have problems. Oh, Vijay. What question? KA. And here you have no KA2. No, right? Yes, you have no. Make star KA2.
It will not.
2.
Okay.
Check.
No, I don't think it will. Oh, sorry.
There is a computer engineer paradox. In our office, some computer was not working. So the computer engineer came, switched off, and it began to work. But when he went off, so he works only on its own errors. Okay? Who has questions? No, that's good, but not very good, because this is an unpredicted result. Oh, you may call. Yes, of course. If it's so, then I take my words back. Okay. So can we proceed further? We understood what are the graph-directed systems. Yes. There is one more interesting thing which I touch. I will not touch in detail. Maybe I will touch it in detail tomorrow, but not today. So, as I already said, very important condition is open set condition. Yes. So, if K is S1 of K union Sm of K, the system satisfies the open set condition if there is such an open set, all that it contains union Si of O, and if Si of O intersection Sj of O is empty if I is not equal to J. This condition guarantees that first that Hausdorff dimension of the fractal is the same as similarity dimension and is the same as in box dimension. All these dimensions coincide. So if we have a graph-directed system, we also need to formulate open set condition for graph-directed systems. The open set condition for graph-directed systems looks the following way. So, but we need to define graph-directed system. Yes? So if you have one space, then we have several maps sending this space to itself. Yes? But if we have two spaces, we have already several maps sending first space to itself, several maps which send second space to first space. Yes? So suppose we have x1 and x2, two spaces, yes? And we write an equation. K1 is S1, 1 of K1 union S1, 1M, 1 of K1, right? So we have several maps which send K1 to itself, yes? And union S2, 1, S1 to 1 of K2, union S1 to M1, 2 of K2, right? This way. And similar equation we have for the second copy. How can we imagine such a graph-directed system? So let us return to our example. We have very nice example. We have just two spaces and just 1, 2, 3, 4, 5, 7 maps, right? So we have K1, I will draw the picture. So we have S1, 1. I can just so I have S1, S2, then map, this will be S3, this will be S4, just for simplicity. This will be S5, S6, and S7, right? There are maps. So what kind of equation we have? K1 is equal to S1 of K1 union S2 of K1, yes, and union S3 of K2, K2 union S4 of K2, yes, and similarly we have K2 is equal to S5 of K1 union S6 of K2, K2 and S7 of K2. You see, suppose we have many spaces and many maps. How to express all this? So we can, for example, in this case we have two spaces, yes? First, and we have two maps from first space to itself, right? Then we have two maps from second space to the first space, right? Then we have one maps from the first space to second space, yes, and we have two maps from second space to itself. So we have a directed graph. So to express the relations between these components, it was invented by Malden and Williams in their paper. I can cite it and can put it. So this is called graph-directed system of maybe similarities or contraction maps, or simply a graph-directed system, and the attractor can be written as a system of equations. So in that case, we need to have several open sets. So if we have two components, we have the sets O1 and O2, and we have that S1, 1I of O1 intersection. So as how to write it? Okay, so we have vertices of the graph, right? And we have edges. So each edge has its origin and its end, yes? So we have that KU is union of SE of K. So if we have edge, then it has beginning and the end. So it will be alpha of E and omega of E. Yes? So it will be SE of K alpha of E, but U is equal to omega of E. So we express it in this way, and we can write very complicated graph-directed system in this manner. Yes. And in this case, we have a set of open, family of open set OU, where U are all possible vertices, yes, and they must satisfy that union of SE K alpha or O alpha of E must lie in U O omega of E, and they need not intersect each other. So there is also, and in this case already, if the graph-directed system satisfies open set condition, then all the components of its attractor will have one more problem. We need to define the similarity dimension for a graph-directed system. Yes? And we need to define good graph-directed system. So the graph-directed system must be strongly connected. So this graph should be such that from any vertex to any vertex we have a path. So any vertices of this graph can be connected by a directed path. So I think we will discuss it later, because but I need to turn to my presentation because I was explaining this thing. So multi-zipper is the graph-directed system of similarities such that images of pairs of points corresponding to different components of these multizippers will be arranged in paths this way. And this will be a multizipper. So we can construct a multizipper whose components will look the following way. It's easy. It consists only of 1, 2, 3, 4, 5, 6 maps, which were 4 of them were defined in your programs, and 2 of them are not defined. You see? So consider so let us observe the time. Really, I don't understand what is the timing, and when we have a break. What? Today we finish at which time? 4:30. So we have 15 minutes, 20 minutes. Okay. 20 minutes. What can we do in 20 minutes? I can maybe I will not consider this example, but I will show you how to build dendrites. I must explain what is a dendrite. A dendrite is a continuum, locally connected, continuum which does not contain closed simple closed curves. So a dendrite is an acyclic continuum. For example, what does it mean? For example, Sierpinski gasket is not a dendrite because it contains a cycle. Yes? If you have self-similar sets whose attractor is connected, then it is locally connected. Yes? So for self-similar set, this condition is satisfied automatically. if the space is connected, then the attractor is locally connected. You may ask me, is it possible to construct a continuum which has no closed curves, but which is not locally connected? Understand, yes? If somebody can imagine that, please tell me. Yes. Okay, can you imagine a continuum without closed arcs inside it, which is not locally connected? Do you remember an example of a self-similar set which is not locally connected? Yes, it's a product of counter set and interval. But you can take this counter set, I will draw it schematically, take a point and draw lines connecting the points of counter set with this vertex. So you get a counter fan. Yes, you see? It doesn't contain any cycle, right? But it is not locally connected because you have infinite number of this rays which are approaching any of these points is accumulation points for the other. All the points are limit points, therefore a neighborhood of any point is homeomorphic to a product of counter set and interval. Yes? Okay. But this is not a self-similar set. Self-similar set can be of such nature. Yes? Self-similar sets, if they are connected, they are locally connected. So our problem will be to construct a locally connected self-similar sets without cycles. So there are some classical examples. First example was invented at the very first years of fractal geometry. It was invented by famous Hungarian mathematician Tamás Vicek, who has several thousands of citations of his works. Yes. So if we take 1, 2, 3, 4, 5 squares, then we get the Vicek set. And Vicek set will be a dendrite. How to prove that this is a dendrite? So I will tell you a dendrite criterion. Let K be a self-similar set. And let K satisfy the following properties. But this yellow wasp is still flying near the blackboard. Okay. Let K be a self-similar set. Which possesses single intersection property property, and let the intersection graph of K be a tree. Then K is a dendrite. You see? Very simple theorem, yes? But I need to explain what kind of intersection graph I keep in my mind, so that you could keep this notion in your minds too. So consider this Zwischek set. Yes, it has 5 copies, right? So we make a graph with 5 vertices, yes, but we will make a more detailed intersection graph, because each 2 copies intersect in 1 point, right? And we add this intersection point as the black points of this graph. And this graph is a tree, right? This graph is a tree. I don't understand what time limits I have today. So we finish today. Yes, I hope to prove this theorem today, but now I hope to prove this theorem tomorrow. And this is the most interesting. There are several interesting theorems which I wish to prove, and then K is a dendrite. Yes. And we will prove this theorem tomorrow. Yes, because this theorem considers the systems of continua which possess single intersection property. As you understand, if we have a dendrite whose copies intersect in 2 points, then this is not a dendrite, because there will be a loop. Yes. The only possibility for copies of dendrite to intersect, they can intersect in a line, or they can intersect in a subdendrite. At first, it seemed to me impossible how to draw a self-similar dendrite whose copy intersects in a subdendrite. But we succeeded in that. I will show you how it was made. Just file, open, Can you wait for 2 minutes? Because I need to find this file. For that reason I need to feed my laptop, because it cannot wait for 2 minutes. Yes. Star open file on. And then Unfortunately, I can't find this file without unswitching this. So, oh no, this doesn't work. And what is about that? I will show you one more very interesting example. Do you see the picture? This is an example of a dendrite, also a dendrite, whose copies intersect in a in this set. You see? Do you see this black set? You have 2 copies. One is this rose color and second is yellow. And they intersect in a set which is a cross. Yes. So, it's wonderful, but it is possible to construct for any kind of polygonal tree. It is possible to construct a dendrite whose copies intersect in this polygonal tree. Yes. This is a very good result, but it is still unpublished. It is still unpublished, and it will be... Sorry, again it doesn't work. And this is also good. Yes, so we can intersect them in a tree. But I will explain how to make a dendrite which will intersect in a subdendrite. I cannot find this file in the time which is left to me, therefore I will explain you how to do this. And we will positively construct such a structure in closest days. For example, consider a dendrite which has 4 copies. This way. So I have some kind of a rectangle and also one rectangle 2 and a rectangle 2, and all these are images of this large rectangle. Yes, and the central rectangle is also here. Yes, so this will be a version of Wittig set. Yes, which slightly change when an elephant presses. So it can be extended to a dendrite constructed from hexagons, right? So you can draw 1 hexagon, then we can draw second hexagon, one more hexagon, and this hexagon. Yes? And imagine that there is a hexagon too. But we don't add this copy here, we have only these 2. And then we forget about this hexagon because we take this set and rotate it 2 times. Rotate it 2 times. So we'll have here one copy belonging to one hexagon, the other copy will belong to the other, and one copy belong to this hexagon. Yes? So we'll have two copies intersecting in a such line. Intersecting in a such line. But if we make different angles, we can have several copies intersecting in a subdendrite. And I will explain, I will explain it to you tomorrow, because now I have 1 minute, and this is my gift to you. This 1 minute is yours. So goodbye, see you tomorrow.